Okay, testing. There you go.
Good morning.
Get up early.
Good morning.
Good morning.
Or good afternoon for you already, Anna.
Yeah. Good morning. Okay, we'll just give everyone a little bit of time. Let me see how many people we have here this morning.
Morning.
We have 21. Okay. Okay. I think we're ready to go this morning. We're going to finish up what we didn't get to yesterday. We're going to talk a little bit about rapid concept development, and I'm also going to blend in a little bit of the intelligent fast failure so we can make up a little bit of time here. And then we're going to skip straight to Flavio and Eric. They're going to talk a little bit about the modeling and simulation. Does that sound like a plan, Anna and Eric and Flavio?
Perfect for me.
It's okay.
All right. Okay, so I will go ahead and share my screen. Okay, and I'm going to be enabled here in a minute. Okay. Okay, here we go. Thank you. Okay. So yesterday we left off and Anna went through several of the phases for the ICED methodology. And where we are right now is the fun part. It's the part I like the most. It's when we're actually going out there and we're evaluating our ideas. And how do we go about doing that? We have a term, we call it rapid concept development. We use a lot of really cool techniques like set-based design and things I learned when I was a researcher at NASA Langley Research Center. And so we're starting with dozens and dozens of ideas, right? And we want to go through this process where we're designing intelligent tests so that we could rapidly evaluate all these different ideas as quickly as possible. And we want to make sure that we understand the types of tests that we're doing so we don't lose any good ideas. We don't throw them out for all the wrong reasons, okay? So I'm going to stop my slideshow now. Okay, so we talked a little bit about when I first introduced you to the ICE methodology of how we construct knowledge as scientists and engineers, and then how we use this building block approach. Okay, so we're going through this analysis experiment loop that we're evaluating these experiments. And these experiments are designed at multiple different levels, at a laboratory level. And so what I tell my students when they're first looking at their ideas, they have ownership of this idea because it's their idea. And we need to train those students to look at these ideas objectively, to look at all the different ways this idea could fail, all the different pros and cons of each of these ideas, right? And so we want to find, when you look at your idea, you look at it and you think of what is the most likely way this idea could fail that we know of. And you immediately want to start addressing and testing that idea in as accurate an environment as you possibly can to get some sense of whether or not this idea has a chance of working or not. We design these very small tests, we do some simple analysis, and we run these tests quickly. And so we call this learning how to fail smart, fast, small, cheap, early, and often. And we did this with the cryogenic tank concept that we talked about. That was a case study that we ran. And we showed you how an entire program was canceled because of that. And then as you're building up your concept and building it up larger and other components that interact with that concept, you're modeling that, you're getting a better and better understanding of the full-scale operation of the system, and you're modeling it at each one of those stages and testing the failure, okay? So we talked a little bit about designing that repair system for the wing leading edge. How do we come up with a concept that could solve this problem, right? But it's not only a very large hole in a wing leading edge that could cause the catastrophe. What we learned after the Columbia accident was that even a thumbnail-sized piece of coating loss on that wing leading edge would create a hole in the wing leading edge that would grow as it gets heated up coming in from orbit through the Earth's atmosphere, okay? So we had to look at repair techniques that could satisfy all those different concepts, right? And had to work. So there are hundreds of people working this problem at NASA and at several other contractor locations in industry. So what we do is when you're generating dozens of ideas, hundreds of ideas, you start to categorize these different types of ideas and solutions, and you're mapping out solution space, right? So a crack repair technique would be if you had a small crack through the wing, you chip the coating, you crack the coating, and there's a potential for that damage to grow. How do you repair that? And so there was a technique that used a gun with a special material that you apply, and then you use instruments to basically smooth it out over the surface of the wing leading edge for that situation. If the hole is larger, some people were looking at what we call patches, basically a patch of the same material like you would do for a bicycle repair that you adhesively attach to the outside of the wing leading edge. For a slightly larger hole or a different type of way to fix a hole, similar techniques that you would do to fix a hole in your wall. You put in a toggle bolt that basically grabs the backside of the structure, and you're cinching down or screwing down the patch onto the wall, okay? And then for very large holes in the wing leading edge, we came up with an idea, which is this system right here, which is a flexible sheet of material similar to the reinforced carbon-carbon wing leading edge material that you could attach mechanically with fasteners. Okay, so those are the different categories of ideas. And when we were testing these ideas, what we learned was that these ideas were failing, and no one understood why these different concepts were failing. And it was getting close to when people wanted to fly. And this is when I went in my friend Don Pettit's garage. Here he is right here. And we started brainstorming and looking at many different ways to solve this problem, right? So told you that networking is very important. And here is where I was creating this Friends of Charlie network, because this was something that I was familiar with. It was my area of expertise. I worked with people around the country that had knowledge in this area. I pulled those people together in what I call a high-performing team. And this is the locations around the world. And the size of the bubble there gives you an idea of the number of people, and the thickness of the line basically is kind of the tightness of connection between these different people on that team. But we're rapidly trying these ideas. Vendors are manufacturing them for us very quickly. They're shipping them to Don's Pettit garage, and we're testing them. And this is kind of the exploratory phase. Not as much detailed analysis, just a lot of testing to understand why they were failing. During this process, we came up with an idea that we thought is a very good idea to solve this problem, and it was a very curved, thin shell made out of this carbon-carbon material. And what our idea was to drill and tap a hole through the wing and basically use a fastener to mechanically fasten that patch and attach it mechanically down to the wing. We had it doubly curved so that as it flattened out, it would spread out and it would be nice and tight with the curvature of the wing leading edge, because there are many different curvatures. And when people were first designing these patches, they designed them very thick and they were very stiff. And so we needed 1,800 of these patches to carry up to potentially fix all the different regions of the wing leading edge. So we came up with that idea. We had this concept. That was one of our ideas. But then what we did was we created a larger team. And this is where you take it to the next level. So we created a larger team. We held the workshop, similar to the workshops we held at NASA, where we teach these teams how to think creatively, how to think outside the box. They came up with many more ideas. And then what you do is you look at these ideas and you rapidly try to mature these ideas. Okay, so if we just look at one of these ideas, the idea that our team came up with, there are many different variations of that concept. Anna presented a morphological analysis yesterday. That's one technique to look at an idea and then look at all the different variations of that idea. Okay, when the program was first looking at solving this problem, if you look at this picture of the wing leading edge, that's a thermal map of what the temperatures would be like at the hottest point when that vehicle is coming through the atmosphere. And so the white region right there is a very small region, and that's where the temperatures are about 3,000 degrees Fahrenheit, the hottest on the wing. So what the program was doing was they were looking at trying to solve the perfect solution, the 100% solution. They were looking at the worst location on the wing. They were assuming the largest amount of damage, and they were going after solving that problem. So if you can imagine, if they didn't come up with a solution to that problem, they would have no solution. And what we did instead was totally look at this problem differently. We started looking at materials that were lower temperature materials, right? So that in other regions of that wing, these other solutions would have worked. And so we developed a whole repertoire of solutions. But what we did was we started looking at these different solutions, these different designs, the curved shell design, the gasket design you see here. And we were also looking at different types of fasteners. And we were doing this simultaneously. Okay, and we were maturing these ideas simultaneously with our team, because at some point, if one of those ideas failed later on in the program, we didn't have a backup, we would have to go all the way back to square one. And what I'm going to do right now is show you an example of why that's important. In one of the slides that two of the slides that I had hidden and forgot to look at. I'm going to unhide. The reason why we do this is because, remember, I forget who presented yesterday. They talked about, Ali DeVec mentioned it. I think Chris Zachney also mentioned it. A lot of these programs fail because they zero in on one solution to the problem very early in the program, that conceptual design phase, and then they get into problems downstream. Well, that was the problem with shuttle. When you look at the shuttle program, this is just one example, and many companies make this mistake and fail. And so they zeroed in on the configuration you see right here after looking at many ideas conceptually, but not doing any real serious testing of those ideas. They zeroed in on one idea, and that's the configuration for the shuttle, right? It had this very, very sensitive and fragile thermal protection system on the bottom of the vehicle. And so they zeroed in on that problem early on in conceptual design phase. And then all of a sudden, as they were flying the vehicle, before they actually flew the vehicle, right? They were getting ready to ship the vehicle from the West Coast to the East Coast to launch the vehicle, lots of tiles were falling off the vehicle, right? And why did that happen? And people were trying to understand why this happened, because when they were looking at the shuttle tile and you look at the strength of the shuttle tile, when you look at the strain isolator pad, which was this flexible pad that the tile attaches to before it's attached to the structure, the strengths were very high. However, when you put that together as a system, the ultimate strength was less than any one of the strengths of the weakest components. And the researchers could not understand why this happened. And so what happened was they had to have a special team, put together a special Tiger team. They did detailed analysis. And what they realized was the fibers in this fabric of the SIP material was sticking in 90 degrees through the thickness, causing stress concentrations in the bottom of the shuttle tile. So they had to go to very intense focused analysis and testing to understand the physics of this problem, the root cause as to why these tiles were coming off in order to fix that problem. And so you see here, the shuttle program was going along, it went to production, and then it was getting ready to operate. They had this problem. And so they had to incur a lot of costs, like orders of magnitude in cost, to basically fix that problem. And so that's why we use this rapid concept development. That's why we teach this in the ICED methodology, because we want to make sure when we select that concept, we have a good backup, but we also have closed all those knowledge gaps so we understand exactly how that system is going to perform. We handed off our idea for the plug material to another team at NASA Langley. They started conducting analysis and fabricating these components. As we were looking at this problem, this is when I asked a good friend of mine, Pete Naffo, to conduct aerothermal analysis of this idea. And as you see here, when you test these plugs in an arc jet, simulated heating conditions, the flow is from left to right. The lip of that plug that's a protuberance to the flow gets heated very high. And this is why these plugs were burning up. When we actually had the expert, the right expert that understood aerothermal dynamics, conducted an analysis in one day, he was able to identify what was causing this increase in heating and how much heating it was. And he gave us the parameters to design that plug so that it would not burn up when we come through the atmosphere. So this is where in our program, we want to show people how to connect with just the right experts at just the right time to solve that problem. And then as you see on the right, we tested this in orbit in 0G inside the vehicle where we have these flexible plugs. On my mission, we carried 13 plugs because they were flexible as opposed to 1,800. And the other thing this team did was we invented the drill bits to actually drill and tap different size holes. We developed the fasteners to plug these holes, and we developed different size patches. At the same time, we also developed the solution to the very large problem. So what we did was we came up with a category of solutions that we could stack together and build together to solve larger and larger pieces of damage. And that was very effective. We did things that people said were impossible. They said it was impossible to drill through carbon-carbon material. And so that's kind of the technique. I have to go through it very quickly, but during the course of the program, understanding how to conduct rapid concept development, set-based design are principles that take several lessons and is almost a mini course in and of itself. And here is where I'm going to hand it off to Anna, I believe. Are you ready to take over, Anna? You see. Anna? We can't hear you. We can't hear you, Anna.
How about now?
Now we can hear you. That's great. Did you want to pick up are there some things that you want to say, Anna, before we turn it over to Flavio and Eric?
I think we could go straight to Flavio and Eric, and then after that.
You'll say a few words? Okay. All right, Flavio and Eric, you ready to continue with the simulation discussion?
Okay, I will share my screen. Just a second. Presentation, screen 1, screen 2. Okay, sure. Is okay?
Yep, that's good. That's good, Flavio.
Okay, so I will talk about simulation environment and how to use that in our project in Brazil. This presentation is I will present in 15 minutes, and after that, Eric Homer will present the next 15 minutes. So I will talk about how to use this to enable human creativity. And the next, I will talk about how we solve some kind of problem to democratizing robotics. To enable human creativity, we start to establishing some emotional connection with the problem. You know, when we have in Brazil, we don't have approach to space and launching rockets, some kind of that, but we have problems with children and kidney disease, and children and with adults with autism, and so to bring these problems to students to solve, we connect the robots with Alexandre is the little one. He has a kidney disease, go to hospital 4 days a week, 4 hours each day. So this robot brings to him some kind of conversation, spend time with some talk, some playing games, but the robot has navigation problems, communication problems, and the other one is Pepper, much more sophisticated robot interacting with children with autism. And
we don't see your slides, Flavio. Sorry, we don't see your slides. Your slides.
no.
No. We see your browser.
You don't see my slides?
No. I don't know if.
So just a second, please. Stop share. Thank you for advising me how I can share screens, and how is that possible? Maybe this one. And now?
Not yet.
Not yet?
Wow. It's coming. It's coming. Yeah. Now, please.
And now, this is not the. No, this is the.
We see the
wrong
part of,
choice. Sorry. Stop share, sharing again, and okay. And after that, and now.
I think yes, it's okay. Now it's okay.
Yeah. Okay. So speed up. This is the presentation, and Eric will present the next 15 minutes. And so we talk about our enable human creativity is to connect the people to create how to create solutions, more creativity. We work with the emotionally connected solutions, bring to the students how to solve the problems to another human being. And this kind scenario, in this first scenario, we have Alexandre interacting with this robot. This robot has many kind of improvements need to do, navigation problems, communication problems, and down here we have Pepper, much more sophisticated robots interacting with autism, children with autism, but has the same problem, navigation problems, communication problems, interacting with the arms. So we take these problems and apply these solutions in hospitals with children with autism and adults with autism. And this uh, this kind of machine are very expensive, and to bring this equipment or robots to the classroom, we need another strategy. So we use virtual environments to replicate this real robots. And you see the classbot here, and Eric, thanks to Eric, we virtualize this robot in our simulation environment. And with virtualizing robots, we can democratize, we can provide universal access to anyone to design, development, and launch real-world robotics application without any kind of real robots in these hands, you know. And after that, we tell the stories to the children in classrooms, and we talk about these kids, about the Alexandre and his problems with kidney disease, and his partner, the robot that has a kind of navigation problem. And we explain how to avoid obstacles using this simulation environment. And the guys, the little ones, has access to the virtual simulation environment, and they solve in groups these navigation problems. And after that, the validation of these solutions is made on this real robot. You see these 4 girls playing with the real robot. And we did the same thing with high school students to solve pick and place. In case we explain about the Pepper, Pepper needs to take some kind of object in place to the other. And the students solve these problems using the simulation, and the validation occurs in the real robot. In the down left corner, you see the kid solving the problem with the real robot. Uh, the process is the same. We emotionally connect these students how to solve problems to the others. And the simulation environment is a kind of a test bed for agile learning practices. We did this 600 with more than 600 students, and we work 100 educators in São Paulo. For this results, we receive this impact badge from Latam Positive Impact Startups from Innovation Latam. We have fund from FAPESP and Centro Paula Souza in partnership with Copilot Robotics. And our startup is strongly related to the universities, because we need researchers like Eric, the next talk about this, his project, and that's it. We think we.
You turn off your microphone.
We lost your sound, Flavio.
The microphone turned off.
And now?
Now we can hear you.
So our strategy is strong connected to the ICE methodology, and I think we have much to learn applying to this in Brazil. If you have any questions, or after Eric talk.
Yeah. Okay. So so the question would be for after. Okay. I'm gonna try to be fast because I think the schedule we're a little bit out of schedule, and my presentation is 2 minutes too long. I'm trying to. I will try to go fast. So share screen.
Eric, don't rush too fast.
It's okay. It's okay.
Yeah.
Okay.
Yeah.
Okay. Perfect. So you can hear me, and can you see my presentation?
Yes. Yes.
This is
yes.
annoying. Let me take that off. Okay. Here we go. So good morning, everybody, or good afternoon for Anna and people from another time lag. I will be focusing on the research, the use of the simulation for the research we are conducting with other countries in Luxembourg and Japan about the planetary exploration rover, mostly to look at the first step will be to look for water on the moon. To do that, I will present the benefit of having a simulator. So the simulation here is a Coppelia sim, also known as VREP. You can see there are like 4 robots, all type of robots: a walking robot, a mobile manipulator, a parallel manipulator, and a more regular industrial serial manipulator. And they are all collaborating or playing against each other, tic-tac-toe and chess. Sharing tools, you can see that the robot in the middle is sharing his tool to take a drilling tool or to manipulate something or to take a pen. And they are all working together with those cameras, looking at the chess and tic-tac-toe, and the camera is doing some image processing to have an understanding on the scene and let the robot decide about the strategy, where they are going to play, and these kind of things. So all the environment is done in dynamic, so you can simulate the dynamic of the robots. Here it's a simple planar configuration, but it could they could have played on the moon somehow, or a rough terrain. So this is a robot called Queens. That was I was living in Japan for a few years, and my last work was to work on this robot called Queens. That was actually the first robot, Japanese robot, going into the crippled Fukushima nuclear reactor after the disaster in March 2011. So the first one to get inside were the robot from iRobot. They had a military robot. This company, American company, had a military robot that was already radiation ready because it was a military robot. About the same design with flippers, not so many flippers, but he was able to drive around rough terrain, but he was not able, unfortunately, to climb to the second floor of the third crippled Fukushima reactor. So after the event, after the tsunami, the earthquake, tsunami, and the explosion of the reactor, this robot was already made, but we had to retrofit it to re-engineer it to sustain the mostly sustained test and sustain the radiations. And once it was done, he was able to climb the stairs where unfortunately the robot from iRobot was not able to go, and to take some measurements. My participation on the project, so it was prior, it was a rescue robot that we had to modify, but my participation was on the design, and especially I focused on the climbing stair autonomous climbing stairs. So you have the flippers here that adjust to the environment autonomously to be able to address the stairs and being able to climb the stairs. To be doing that, it's got some sensors, a distance sensor to detect the stairs and know about the environment, very simple one, and some torque sensor and some IMU. And the problem was the following. The problem was to consider that is the robot will be working? Where should I go? Is the robot will be able to climb the stair? Where should I put the sensors that I have? What type of strategy I can apply? And that's exactly what was done with the simulation. I could test where to put the sensor and have and try out the strategy for climbing the stair. So you can see that the robot lift is the front flippers. When you reach the top of to absorb the shock, it lowers the flippers and successfully climb the stairs. And same thing when going down to avoid the robot to have a hard crash when the last part is reaching the end, like here. You see the robot will be climbing and then tumbling. To avoid that, we absorb the shock with the flippers, and same thing going down. And here is the application on the real robot. So the robot is going front and is climbing the stairs, successfully addressing the first stairs, then is able to climb and adjust the flipper to be sure that it will not tumble. And when sorry, too much. When reaching the top of is detecting the top stairs and tumbling and absorbing the shock. And same thing when going downstairs, it will detect in order to fall hard, the front flipper absorbs the shock. The robot goes downstairs, and when reaching down, it will absorb the shock with, like, to have a smooth ride. So this is how the simulation was being. With the simulation, we were able to place all those sensors, try out the technology, and doing that. Another thing that you can do with the simulation is to plug, and this is my contribution with Coppolia Sim, the company. Especially, I worked a lot on how to be able to put some input and output to the software, not to be just a simulator, but to be able to use the simulation capabilities to have like some hardware in the loop or simulation in the loop. Here you have a robot, a Pioneer robot with a connection with the with Wi-Fi connection to be able to be controlled. You have a simulation of this robot in the same environment, and the simulation is computing all the velocities for the robot based on the input of a Wiimote. So the motion of the Wiimote define the direction I want to go. And the calculation is done here and sent the velocity of the wheels to the robot that is reproducing these velocities while the robot is actually doing some dynamic simulation. And you can use that as a virtual representation of the environment to understand where the robot is. So you have some visibility. If those are remote, you can do something about that. And you have the 3D simulation with a dynamic engine inside that allows you to check, to have a feedback, a regular feedback from where the robot is, because the robot is sending its real position and it's correcting the simulation, saying, no, robot, you're not here, you're here. And in between two updates, we have a smooth simulation of the robot. So this is useful for the simulation is useful for that to try out. Here we have a camera over the robot, and we represent you can see that the simulation environment is the same about the real world, and we do all the calculation of path planning inside the simulator and send the resulting velocities to the robot. Here you have a video feedback. You just click where you want to go. I will be clicking here, and the robot in the simulation knows where to go. I will be clicking here. It will be here, and the robot computes and go to there. So you have a 3D environment where you can put a different way. You can see the robot from a different point of view than just through the camera to understand better the environment. You have a feedback, a visual feedback, and you use all the. You don't need the real robot to make your algorithm work and try out different solutions. So of course, it means that in this case, the the environment was built prior to the robot knows his environment. It's got a 3D map of it, but you can have just the basic architecture built and have laser sensor that adjust and put some along the way some dynamic obstacles, or rebuild or completely the environment. This is another part of the research that I'm not going to present, but that we're working on. So the simulation is clearly helpful to be able to solve this kind of problem of design, and also testing in certain conditions, and also as a visualization device when you are teleoperating a robot. So for our challenge, you will be working on the robotic planetary exploration to find water, and this is actually something I'm doing, and that's why we are building a platform to be able to between Brazil, Luxembourg, and Japan, and we are building this platform to solve those problems jointly. With the simulator in the middle, you are able to try out your algorithm, etc., etc. You don't have access to the robot, so you can do this kind of things. And what are the challenges that for planetary exploration you will be encountering? First, there is the mobility over a rough terrain. So the rough terrain could be hard rock and soft sandy terrain. We have seen that and also under different gravity condition. We have seen in previous presentation during this event that the moon have the water in the moon are deep inside those cold, no light, without light craters. So a crater is what? A crater is a rough terrain where legs would be addressing better than wheels the terrain, but legs are spending a lot of energy to be activating. Wheels are okay, doing a better job and with using less energy when on a soft terrain like sandy, regolith type. So you can have like tracks, like it's the case for us, which is a compromise between legs and wheels. We can have hybrids, being legs with wheels together, working together, and other solution like flying and this kind of thing eventually. So those are the kind of solution that has been that mobility brings, but each of them have plus and minus things that you need to try. And probably you have like other type of solution like we worked on with Anna yesterday. You need mobility to research about the mobility. You need to research about the control and sensing, what kind of sensor you will be using, what kind of motor you will be using, how you would be actuating, controlling the motor to avoid like when you go straight in a slope, traversing a slope, and there is a sandy, it's a sandy environment. You go straight, but there is some kind of drifting that you could control with to avoid the robot to get stuck or to go straight. So this is another kind of challenge that we can solve, that we need to solve. Localization and mapping are very important because the robot needs to know where it is in order to plan to go where it decided to go and successfully do that. And also the map are important because within the map along the way, you will be mapping and also finding where the water is. So you will be needing to report that we have water in this area of the crater at this quantity. And this is the kind of things that's the mission. The water prospection would be the mission. So we need to have a good map and a good localization algorithm. And also, and you will be working on that, exploration strategy, how to explore the environment properly, the action and past planning to do that, especially if you have several robots. Yesterday was presented the ants, like small robots with a small capacity, but working together. So this is something that we can think about to maximize the coverage of the exploration. Having several robots working together remotely, communicating together, and maybe having an emergent behavior like ants, in order to be trying out to look around the environment. This is very important, and you can do that with a simulation. Is nicely done because you just don't need to have the robots built plenty of robot builds. You just copy paste the instance of the simulation and the robot on the simulation, and you can run the simulation to try out those strategy even before having the final version of the robot. So everything is to work on parallel, like Charles was explaining, and that allows you to be creative, to be testing, to have several people, several groups working together to realize these kind of things and select at the end the best, the solution that is working the best. And of course, you have to be able to test the final version of the robot under realistic, or not final, not only the final robot, but sorry, Charles, you just said that you needed to test regularly, plenty, cheaply, etc., etc. And so you need to have an environment to be able to test that. Several solutions. So you could either have a test bed, which is, for instance, we're trying to reproduce the Martian or the lunar condition, where you can put your robots on and drive around. But for the test bed, is as you are not testing on site, you have a gravity issue. So maybe having a system that will hold the robot, the center of gravity of the robot, to lighten up, to simulate. To emulate, sorry, some gravity conditions. It's not the ideal, but it's the best you can do. And the simulation would be a part of it. But for the simulation, you need to have some extra. Copolyacim doesn't have it yet, but we're working on implementing that, like thermomechanics properties. What are the properties of the sand, the regolith over the environment? What is the environment? Is how the environment is changing when you are driving over it, and how the environment is impacting the forces, applying forces on the wheel, on the robots, on the robots. How those are things under those gravity or microgravity condition you need to be aware of and testing. So simulation can be useful in this situation. So that's why we're developing for our project this platform, which is for research, development, and education. To be able to have a common, based on the simulation, to have a common working tool to link the work of Japan, Luxembourg. In Japan, sorry. In Japan, Professor Yoshida is the CTO of and founder of iSpace. That is the company, one of the finalists of the Google Lunar X Prize. He's also a professor at the Tohoku University, where I did a postdoc. He was my boss for a few years. So, and I was actually the one telling him about the Google X Prize. And he did that. He entered and become finalist. So in his lab, they are working a lot on the hardware, developing robots and how to control those robots, the robot hardware and this kind of thing. This is one. This is actually the robot I designed for lunar exploration, hybrid one with legs and wheels. It's a multicultural team, also always having like foreign students, and they developed a lot of different solutions. And this is the robot actually that a version of the robot that they will be sending in 2022 to the moon to look for actually first to drive around, and future mission to be really looking for some lunar water. Next year they will be testing the lander. Hopefully, they are developing so they're working on that, and also thermomechanical models to be able to modelize how the ground is having effect on the robot's motion. In Luxembourg, they have a big test bed with a motion capture system, where they also have an interdisciplinary space master program, and I will be doing my best to try for them to include the ICED methodology into this stuff, into their program. That would be, I think, perfect. I already spoke with Miguel about that. Anyway, probably there is something to do there. I'm looking at you, Charles. They are working on rover mobility validation, and they are working on design, and they are working also on the thermomechanic model estimation parameters. So they have this big lunar emulation part that we are trying in Brazil to modelize, so that and include into the education the platform, so that everybody can work together on the common. So the robot from Japan inside the lunar testbed of Luxembourg in the simulation developed in Switzerland and Brazil. to be able to work on different type of issues at different level. That would be like PhD research, like on hardware and control or localization mapping on the moon, terra mechanics modeling. It could be master program also for the hardware, here also for the sensing and simulation, developing this kind of thing. And also high school project to work on the human-machine interaction, to work on some robotic designs and this kind of things. And actually, those are already effective. We already did some stuff, like this is not done, but the idea is to, take it off. So to work on the deformable lunar terrain inside the simulation, to train with machine learning algorithm, because machine learning is based on repeating and repeating and repeating and repeating millions of times the simulation, the condition of the robot to be able to learn. And you don't want to put the robot back and forth in the same condition millions of times. So if you have a simulation for that, to do it, it's much better. So you can try out and the robot will learn by itself. And I have at least a big, you reduce the space of solutions drastically with the machine learning inside the simulation. And then you can try just with this reduced space of solution on the real robot. So this PhD that didn't start yet would be about like finding landmarks to be able to localize itself and map the environment. Also look at the trace, the marks that the wheels, if it's wheels, living on the environment, in order to be able to know that, oh, I should be going straight, and I see that I'm deviating from my trajectory. So I can use looking at the marks on the on the ground that I'm living in the regolith, I can correct these kind of things with visual odometry and to detect the slippery, which is one of the challenge. But also working on implementing those, synchronizing the test bed with the simulation, with the form of the shape of it, so that we can work on the same ground between the different countries, and also having the same simulating the same terra mechanics properties on the ground. Actually, on the real moon would be better. But all this is a PhD student that will be doing. This is the work of a master internship program. The student was French in Japan, and I was supervising him from Brazil. He worked on this robot that is a robot from Japan, from Professor Yoshida, with this spatial suspensions device here, and he modelized that in the simulator to be able to test, so that we can extensively test the claim that the robot would be able to drive faster than usual robot at up to 1 meter per second. It's not the case in the simulation here, we go slow, but showing that. And also implemented a very simple version of the terra mechanics properties using a simple model to apply forces on each wheels, extra forces on each wheels, to simulate that the motion on the sandy terrain. And this is my final slide about that was also conducted 2 years ago. 3 high school students were working on implementing a research that I was working on, a hybrid leg wheel robot. They implemented this design, 4-wheel robot, steering robot, 4-wheel steering robot, that the wheels are actually legs, and they developed the hardware and the software that are in high school, end of high school. They developed the software, even the interface. So you can see the robot is walking, and you control it with the motion of the hand, going forward and backward to move the robot forward and backward. If you want to turn, you rotate the hand, and then the robot is walking and turning on the left or and on the right. And if you close your fist, the robot will transform his leg into wheels, and you can drive it. It's going to do that now. Okay, so it's wheels, and they can go drive forward, backward, turn, etc., etc. Also, what they did as an extension, they use some capabilities of VREP to have a virtual reality environment, so you can actually be present and see in the environment. You can see the robot as if you were like there, so you can understand better and see better what is happening and explore the environment in a better way. So if the robot is having some capabilities of making a 3D model of the environment, as all the exploration robots are doing on Mars or the Moon, you could actually use this data to navigate So to help to motivate children to be looking forward to work in this kind of thing, because this is so cool. You are on the moon with 3D pictures that are actually the picture mapped on the 3D environment where you can move around, and this is great also for showing off what the results to the public. So yeah, and that's the robot. During the expositions, I had to develop to show to show the results in a exposition of the results. So they are like also showing, explaining to everybody, and they have like the 3D. It's difficult to show, but this is where you can see that there is the moon here, and it's in 3D. So those are the possibilities. Everything is possible in there, even because of the simulation, thanks to the simulation and the common platform. So this is, and there are again high school students, very good high school students, but still high school students. So the link with today's is that this simulator is behind NTU's Blocky programming, so that fits perfectly the ICED methodology for this challenge. We will be working on different type, using the same robot, but the possibility of changing the wheels for and being creative to make your own mobility solution, working on your own. Today you will be working on the simple strategy to explore the environment and these kind of things. So all these features depend on the simulation, and you can participate to the development of more features of the framework. By, for instance, having the possibility to put like more Terra mechanics models. This is what is lacking the most. Terra mechanics model or new sensor or new. It's very easy to develop that in the simulation and add that to the platform to be more creative, having your new your very own mobility device, a new type of wheels or whatever that you will implement into the system, into the platform, and we can use that and have fun with it. And that's what you're going to do. You can have like middle school and postgraduate research development and challenge that fit perfectly the ICD methodology, as I said. And today you will be working on some of the few challenges. Good luck with the challenge and have fun. I am way over my 15 minutes, I guess, but I'm sorry about that. But that's it. Thank you very much.
Can you hear me, Eric?
Yes, that's perfect.
That was phenomenal.
Oh, thank you. Wow.
Okay, we're getting a little feedback.
Let me turn.
I think it's on our end. Okay. Nope, we still have it. Okay. Testing. Okay. Looks like it's working. Okay. What, can you hear me now?
Yes.
Yes.
Okay.
Yes.
What I wanted to do, first I want to ask if anyone has any questions for Dr. Roma or Flavio. Does anyone have any questions? Okay, before we go to Anna, and please, if folks have questions, send them to us, and we will make sure that the different presenters get those questions and answer those questions. But one of the things I wanted to point out, and the reason why we love working with our partners in Brazil, NTU, Capillia Sim, and Dr. Roma, is because he showed you in a very short presentation how these problems can be worked at a pre-K level, when Flavio was showing in the hospital, all the way to graduate school and postdoctoral work, right? And the importance of why you need to do that. The other thing that was missing in a lot of these educational programs around the world, right, is that we have these great programs like FIRST Robotics. But where is the connectivity and measurement of what the students are learning and where do they need to go next in order to expand their skills to be able to solve these really epic challenges, really designing a robot that will actually work on the surface of the moon and Mars, right? And so what you want to do is you want to be able to encourage these kids at a very young age, which is what Eric is doing in grade school. And you want to show them the path of what they need to learn next and how they learn that, right? And so you see a beautiful program laid out here, and in red, green, and blue, you notice the connectivity between high school, graduate school, and undergraduate school, right? And so what we are trying to do in the Epic Challenge program is really make that connectivity, right? And let these kids explore and have fun, right? But then what we want to do, we want to get them to explore their creativity, but we want to show them how to solve these problems. And that's where we want those students, the students that are just several years older than them, that have learned those skills, that have practiced those skills, to be the real mentors, to help them learn in a very safe, psychologically safe environment. It's okay to fail. It's okay to ask not so smart questions, maybe, that people think, because you're doing it to a near peer, someone that's almost your age that will guide you in this learning. Okay, so that's the beauty of this program. That's why we think it's going to work. That's why I believe it's going to work. And by having the simulation, the modeling and simulation capability allows people to explore that creative landscape, that design space, and use their imagination and fail safe, smart, fast, small, cheap, early, and often. Okay, now I want to stop sharing my screen. I just wanted to make those, reiterate those statements. Anna, do you have anything that you would like to present before our next speaker?
Yes.
Okay.
Yes, I do. So we would close this rapid concept with a few slides that I want to show, and then we will go back to the concept evaluation and do some activity together again. So that's what I would like to do in the next 30 minutes.
Okay, do you have,
Everyone's ready.
you're gonna share your screen?
Yes, I will share my screen.
Okay.
Okay, so you can see these are the same slides that I showed you yesterday before we just, before we decided that we are going to move this for today. So I would not like to repeat them. You will get the slides, so you can go there and look at this material. What I want to just mention is that later on today, I think if I remember the agenda around after 2:15 Florida time, you will have time to start doing those experiments. So just keep in mind what you have heard today now from Charlie and also from Eric about what are those experiments you can do in the simulator, what are those experiments that you can do with the real robot, and how to design those experiments. But what I want to show you maybe just before we move is just to give you a few ideas how you could, when you're designing your course with your students, just a few of example activities of what you could do with them. We really see from experience that it is really, really useful to actually teach them how to design experiments, and then together as a team choose which experiment they will do together. And after they do the experiments, that they also share the results of that experiment, and at least try to do as many experiments as possible, but at least 2 rounds if you can do it. So one maybe round that is of an experiment with less complexity, and then at least another one when they a little bit expand that building block approach, right? They build a little bit more complex experiment, And then finally test also the final prototype that they will come up with. Okay, and now we start the plan for today's day, which was actually to go a bit back and talk about decision making and how do we teach our students and how do we make decisions that are objective. So just to remind you what we talked about, where we were, right? We presented the challenge, then we defined the problem a little bit better by using functional abstraction and decomposition. And there I encouraged you to think about what level of abstraction you could include within your class, within your school. Will it be just a simple level of decomposition, or would you go deeper into understanding those processes and functions? Then we did problem immersion, where we realized what is it that we don't know. And then we went to find answers to those questions. And we started working as a team. And then together, we talked about a lot of different kind of creativity methods. And we tried out one method, which was the morphological analysis, together to generate a lot of concepts. And just now we kind of jumped to this rapid concept development that Charlie and Eric talked about. But now I want to step back one step and talk about the concept evaluation. So imagine from this table, you have created a lot of concepts, but how do you now decide objectively which concept is good, which concept is not good, which concept you should mature more, how much you should mature, and so on. So there's many techniques to do this. And, you know, some of maybe some most obvious techniques would be, you know, just take those concepts and run an experiment and see which one is better, right? That could be one. But sometimes these experiments might be costly, time consuming, you know, resource consuming. So maybe you want to think about other creative ways that you can evaluate your concepts. For example, you could do mathematical modeling, try to model something, right, before you actually go to real world and test. So maybe that will narrow down your set of concepts. Or you want to maybe build a simulator and run tests in the simulated environment. Or what if you could even use some other evaluation techniques that, you know, would maybe take just a couple of minutes so that you could just use pen and paper, so you don't need anything else, you know, and try to narrow down the set of concepts like that. And I would like to present to you one of those techniques that, you know, we don't need to build anything, just a simple table, just as we did before. And so I will give an example, and then we will together try to apply it on the problem of the rover that you have. And the method is called the Pew method. So the Pew method got its name by the creator. That's why it's called like that. And I just want to, okay, like this. Sorry, I'm just changing my Zoom so I can see you better. Great. And what this Pew method is, it is actually a relative evaluation technique. So basically what it needs is it needs a reference concept. And what you do in this method is you compare your concepts that you have generated to this reference concept. Now, how do you compare them? Well, you compare them by having requirements. And you remember when we defined the challenge, I have said at the very beginning, what are the requirements? So those requirements, they're not just there to help you understand the problem, but they're also there to help you evaluate whether you are on the right track with your concepts. So this is where you could use those requirements. And then this method also requires you to put a weight, put a certain importance to these requirements. So, and you know, in the end, you do the evaluation, you calculate the total points, and the total points will tell you which one of your concepts is performing the best. So let's try to do this together using the same example I have given you yesterday. So we had this family vacation problem we divided it into 3 sub-problems: where to travel, how to travel, where to stay, and what to do. And then we generated a lot of ideas. And from these ideas, we can now generate a list of concepts. I just here selected 3. So basically, if I take a car and we sleep in a hostel and we go to visit museums, this is one solution to the vacation problem. And there are other alternatives. But of course, from this table, this list can go on. You know, there can be a lot of different concepts. Now the question is, how do we compare these concepts? Well, I haven't given you yesterday requirements, right? So that was not really a very good definition of that problem. So in order for this method to work, we need those requirements. So here they are. Let's assume that for this example, what we need, we want this vacation to be cheap. We want it also to be quite short, because maybe we don't have time, let's say, just for the sake of having it, you know, as a problem. But we want at the same time to maximize enjoyment, and we also want all of our family members to participate, right? So the most of us can have fun. So now this Pew table, I will exit from here, starts to look something like this. I will delete this. Okay. So I just place these requirements in this column. Those are the exact copy. And then I assign importance to them. Let's say maybe for me right now, the cost has the biggest importance. So we use a scale from 1 to 3. And maybe the enjoyment has the least, but still the participation is somewhere in between. Doesn't really matter. This is something that you would discuss with your team. And when you know your challenge details, that's how you will define the importance. But now the big question is, what should be the reference concept? Well, a reference concept should be something that exists, right? Should be something that we know that have already worked in the past. Maybe it's not solving exactly the same, 100% the same problem that we are having, but it has been working in a similar situation. So let's imagine that that was a vacation we had in Lapland, where we went with a car and we slept in a hotel and we visited Santa. That was the best vacation we have ever had. So now what I do is I place here the concepts. So these are the same ones that I listed here, these 3, and I will start evaluating them. So, you know, you're also very welcome to jump in and comment here. But basically what we now want to do, we want to say whether this concept is better, then we put +1, whether it's the same, we put 0, or whether is worse, then this reference concept for this particular requirement. So let's say taking a car, sleeping in a hostel, and going to museums, let's say that it was cheaper, because a hostel is cheaper than the hotel, right? Let's say time-wise, maybe it took the same amount of time. Enjoyment, let's say maybe they didn't enjoy so much museums as they enjoyed Santa. And well, maybe because of the Santa and the hostel and maybe the participation will also be lower. So let's put also -1. And then what we need to do is just multiply. So we multiply the scores, the evaluation scores, with the importance, and we sum them up. So 3 times 1 plus 1 times 0 plus 1 times -1 and plus 2 times -1. If I calculated that right, it should be 0, right? So we do the same for the other 2 concepts, and I just skip forward. Let's not go. So you follow the same logic. And like this, we will get actually objective measure of which concept is the best. So it seems that this concept of going with the plane, sleeping in a tent and sightseeing is actually performing the best. So this means this concept we can take to the next phase. And like this, we can repeat this for as many concepts as we have. So I hope you could see how this method gives you that objectivity, where you really look at the requirements, you really look at the concepts, and you evaluate. So what I would like you to do is now spend the next 13 minutes, we don't have 15, but we have 13, to take, yesterday I asked you to generate 2 concepts from that morphological table. So now take those 2 concepts and compare it to the reference, which is let's now use as a reference the robot that we have actually selected for you for this challenge. And then use the 3 requirements that I have posed to you in the very beginning. So robustness and avoid collision, minimizing the time of operation, and needs to be built in the minimum time. Assign weight, assign evaluation scores, calculate the total, and let's see if some of the ideas you came up with yesterday score better than the one that we picked for you to play with later. So let's take now 12 minutes to do this exercise. I will leave this on here so you can see the table. And let's just get back after 12 minutes. If you have any questions, please ask at any point. I'm here to answer.
I see someone took a similar vacation to you, Anna, if you read the chat box. And I definitely want to go visit Lapland and see the real Santa Claus also.
Yes, it really is a life-changing experience. Santa really has this ability to bring somehow the joy back to your life and energy. Even my mom was inspired when she turned 70. We went and she was like, oh, I have to be now very good because there is only 6 months till Christmas. So
but
right.
Anna, where is Santa from? Which country?
Oh, from Rovaniemi. From Rovaniemi in Finland, of course.
Already, are you sure?
Yes.
All right, so we're going to let the teams work. And after 12 minutes, we're going to come back and maybe we'll present someone's solution or someone's evaluation. Okay?
Yeah. Yes, sounds good.
Excellent.
Anna, I have a question. Can you hear me?
Yes, ask.
Okay. Yes, for the so it's +1, 0, -1. But if we do that, we are not comparing the concept between each other. For instance, maybe my concept 1 and 2 have are better than the reference, so +1. But the concept 2 is better than concept 1. Is that in a new iteration of the process that we can define that, or what is the way to differentiate concept 1 and 2?
Yes. So of course, because these concepts yet don't exist, it's really hard to compare whether they will work or not.
Okay.
That is
Sure,
the idea
sure.
that we have some reference that exists.
Okay, okay.
So you can compare to that. But yes, what you're talking about, it might happen like when you, because now you're looking at these concepts through the lens of these requirements, right?
Yes.
So it might happen that, let's say, let me see here. Maybe I know that this is a better concept. I have some gut feeling that it's a better concept, but it scored less than this, right? And the difference was really minor, just 1 point, right? So now I could look into these requirements and I could see that, okay, where did this 1 point difference happen? It wasn't happening for all the requirements. Maybe it was happening under one. So let's see here. Maybe it happened here, right? So now I can start to think, okay, if this concept actually was better under all other requirements, but this one, could I somehow improve this concept a little bit so that it would, so could I take something from this concept 2 and put it in my concept 1 to make it even better, so that then it would be the best. So you could do this second iteration where now you use the first iteration, you see what's happening, now you update your list of concepts, you improve them based on what you learned from this table as well, and then you can do the next iteration and like that.
Okay, so it's an iterative process where you are not comparing the concept between them afterwards in the iteration, as one concept one becomes a reference concept, and etc., and concept 2 becomes a stale concept, but you are modifying you're modifying the concept itself to be compared in the same way, right? So for instance, okay, this part, for instance, we could take the plane in concept 2 and switch with the car and put instead of the car in concept 1, so that the minimizing time will go faster. So we minimizing time and we get a better point, not 0 but +1 in there. That's the idea, right?
Right. But notice, also because I assume that in this phase, what we did, we were very early in the conceptual development. So really our concepts might be something really that, might not function, doesn't exist. So that's why we compare to something that is existing. But this method equally works if you just want to compare ideas that exist already and you want to compare them to each other. You can do that, of course, as well, using the same method. So just one of them would be the reference, and the rest would be what you compare with.
Okay, perfect.
So it's possible to do that way as well. So many ways to use the table, and you could see, like, when you design your course, depending on how you design it, then you can adjust, if you choose to use the Pew table, adjust how you use it.
I see. Thank you very much.
Sure.
Makes sense.
And just the time, maybe we have time, 2 minutes left.
Any other questions for Anna? No? Okay, well. And once again, this was only one evaluation technique. There are many different types of evaluation techniques. These are multi-objective function optimization problems, right? And so you can explore different techniques for evaluating ideas. And once again, don't just select one idea. continue to mature the other ideas, maybe use some of the parts of the other ideas into your solution to merge the ideas. What we're going to do now during our lunch break, we have another speaker who is an intern that we have had at the Epic Education Foundation. He was working with Joe Russo, our Chief Information Officer, and you heard a little bit about the importance of selecting the team. And we didn't go into it in a lot of detail. It's very complex how we do that. And this is one idea that we were looking at to use in order to help select the members of the team and for these student teams. What we do in the Epic Education Foundation is we want to develop a methodology and an algorithm to help teachers select the right kids with the right skills for the different teams. And so one of the ideas we were looking at was very similar to what the design school at Stanford was looking at. They developed a process called teamology. And our intern, Mr. Etienne Gauthier, has been working with Joe Rousseau, and he coded up an application that our educators can use, and he's going to talk a little bit about the process. He's a high school student from the Leffel School in Westchester, New York. And I'd like to introduce him right now. Step up here, Eitan, and show us what you did for Joe and what we hope to allow the educators to use for selection of the students. There you go.
Can you hear us? Can you hear us? Yeah.
Yes, we can hear you.
All right. Hello, everyone. My name is Eitan. Just before I start, I want to say thank you to Charlie and to Joe for giving me the opportunity to speak. And today I'm going to talk a little bit about teamology. So I know on all teams, sometimes work is not distributed properly. Either some people do all the work, some people do none of the work, or somewhere in between. Yeah. So today I'm going to talk a little bit about how we can maybe fix that. So to optimize team performance, you need to leverage the strength of every member and minimize the duplication of effort. Again, to optimize team performance, you need to leverage the strength of every member and minimize the duplication of effort. So have you ever struggled forming teams for a class project? Have you ever felt that some students are excellent teammates while others can't pull their weight? Well, the solution to this is teamology. Teamology is the construction and organization of effective teams. You ask, what is an effective team? An effective team is when all members know, share, and adopt roles consistent with their preferences with members in each affinity group. That we'll define in a second. So how do we construct these teams without utilizing random team-based methods alone, whether that's picking out of a hat alphabetically or rolling a dice? Well, there are 3 steps. The 3 steps are survey, analyze, and construct. Doug Wild, whose methodology was developed at Stanford University, and they had a lot of success in their engineering team, said this quote, that people who individually have only a few problem-solving strategies can pull these on a good team to make it overcome any obstacle it encounters. So what we created is we created a platform where students are surveyed to identify and categorize them based on cognitive modes to ultimately construct both effective and efficient teams. This was programmed mainly in Python and JavaScript. So how do we do this? So to develop high-performing teams, we need to calculate students' personality types from their responses to inventory questions. So this takes into account the learning styles, understanding, and characterization of decision-making to develop these high-performing teams. So our calculations optimize group dynamics, collaboration, organization, and success by building optimal teams to effectively tackle and solve problems. So the first step is survey. So using the Myers-Briggs type indicator, also known as the MBTI, we are going to survey our students, and then we're going to be able to categorize them into the 4 dichotomies, which were then later split up into the 16 different personality types. So then what we do after that is we use Doug Weil's teamology, and he studied how to make these quantitative transformations from the MBTI scores to the Jungian domain, which has their 8 cognitive modes, which yields these cognitive patterns. So these results, are easier for team analysis and are more suitable for these transformations. So lastly, what happens is we use Carl Jung's theory of psychological types, and he has these 8 cognitive types. So first is E for extroverted, I for introverted, S for sensing, N for intuition, T for thinking, F for feeling, J for judging, and P for perceiving. So let me repeat again. So we first take the MBTI surveys, then we move that over to the teamology, and then we take those and we put them into Carl Jung's theory. So for example, let's say in our surveys, after we do all of our calculations, we determine that someone is more extroverted than introverted. So we do that for all of these 4 types, and then we create these patterns. So for example, this person is E, N, F, and P, and the opposite of that would be I, S, T, J. And like I mentioned earlier, you want people from all different kinds. You don't want a whole team of everybody who's extroverted or a team of everybody who's introverted. You want to have a diversity in these kind of things. So the goal of this project is to really bring all these team members together. So once you have these patterns, they are associated with different roles. So for example, you have process manager, influencer, innovator, or conflict manager. And the goal is to bring all these different people together on the team. So the first step of our program is to sign up. So the way the students sign up is they're going to sign up with a given class code, which you can see is highlighted in yellow. And let's say you're in 6th grade class A, for example, your code would be 1212. And what happens is your test will appear on your dashboard. So for different age groups, you can either have a longer or shorter test. And based on that, your class code, you're going to have a test appear on your dashboard, which we'll show in the next slide. So here's what the sign up process would look like. Students would sign up with their first name, last name, email address, and password. The password we also keep hashed, so nobody can really except the user itself. And then they add their class code so we can have the appropriate test there for them. So you'll see they put the class code and the password, and then they sign up. All right. So students are surveyed using the Myers-Briggs type indicator inventory in order to discover what modes each member has to contribute. So as you see here on the image, when you're on your dashboard, you're going to have these 3 selections. You can have either take your test, download the results, or email results. You cannot download or email your results if you have not taken the test. So here's what the dashboard will look like. Once you get onto your dashboard with your class, you're going to have 1 test there already waiting for you, depending on your age group. So you'll see you're going to first go through and take the test. And there are different questions. You have to decide which one most applies to you. So there are about 20 questions here. This is for the shortened version. And you go through them and pick which one, again, applies most to you. All right, so I'm going to skip this. All right, so the next step is analyzing. So once we've surveyed all our students, what do we do with this information? So there are many different ways to analyze it, but one way we chose to, we'll show you in a second. So first, after surveying students, they're going to receive a customized and simplified version of their results with information for further research. So the entire point of this is that teachers can have their information categorized in a separate way, but the idea is for the students to also understand what process is going on. We don't want to randomly assign them groups and they're like, why am I with this other student? So what we're doing is we're making this simplified version for each student. So as you can see on the image on the right side of the screen, after a student takes a test, they're not going to be able to take the test again. They're only able to download and email the results unless the teacher opens the test up for revision for either the whole class or for a given student. So as users also have an option to either receive their results as an email or to download them on their computer locally. So this is a short snapshot of what the student report would look like. So it's very dense and compact, but it's really meant to geared towards the students so they can actually understand what is going on and what they're most likely applies to. So students will receive this detailed report to enhance their own knowledge and learn more about their own projected efficiency on a team. So now we're going to go through each part of the student report. So we're going to start on the top, which you can see is highlighted in yellow. And this contains more of the macro classifications of the student using the MBTI survey, which also has an image, description, the name, and the URL for, again, further research. So the student can just figure out the first thing. This is what I'm classified in. All right. Next part of the student report is we're going to get more detailed and now to the psychological functions, which you can see is also highlighted in yellow. So the report contains these specific psychological functions of the students with more specific information on their perception and judgment domain classifications. So as you can see in the judgment domain, for example, this person has extroverted thinking, and therefore we have a link there also for further research so they can look through and also learn more about themselves and why they were assigned to a given team. All right, so the last part of the student report is the most detailed part, which is the roles that come naturally to them. So for example, here is the students also receive a table with the roles that come naturally to them with distinctions for significant preference. Yeah, so basically the idea of that is, I'll highlight a few examples of that. So the significant preference is not what might be what they're classified to, but what do we think is the most that they classifies them and what most pertains to them. So for example, here, this person's a methodologist, and the next one here is a crafter, and it has this other information and classifications so they can learn a little bit more about what might apply to them or what might not. All right, so after we do that, each person is assigned, in a sense, to a specific role. So once you have these patterns, you're gonna be assigned to a role, and you want to have one person from each role on every team to get that diversity of thought and knowledge. So for example, you want to have the traits of collaboration, communication, decision-making, and self-management. So for collaboration, you have conflict manager, team builder, and for communication, you have active listener and influencer. For decision-making, you have analyzer, innovator, fact seeker. And for self-management, you have goal director, process manager, and consensus builder. So the idea and the whole objective of the project is by utilizing the full range of information available from the reports that we already analyzed, we're enhancing our understanding of the educational processes beyond the possibilities from existing random team-based methods alone. So instead of just picking out of a hat or doing alphabetically, we want to actually have these teams very effective to actually make these most optimal teams so we can have the better dynamics. All right, so the last portion of this is constructing. So after we already surveyed our students, after we've analyzed their results, we have to see how these students would work together on a team. So using these classifications, we're going to assign the teams. So teams work best when all members know, share, and adopt roles consistent with their preferences. The strongest teams will have members from each affinity group. So again, like I mentioned before, you don't want all teams when everybody's an extrovert or when everybody's an introvert. You want to have that diversity. So the program also provides teachers and administrators with permutations of the most optimal team formations. So for example, let's say student A and student B cannot work well together. The teacher has the ability to set constraints for them not to work there. And then we'd also reassign those teams. Teachers also can set the constraints and also assign their teams manually if they feel more comfortable doing that. So here's what it looked like on the administration side. So for example, the teachers can also edit the information. So you'll see in this short clip that we're going to edit Susan Jones for a second. So you can see we can edit the first name, the last name, the email, the password, and also what's a nice function is you can change the language. So I know there's students not just who speak English, but we can also translate that to other languages. You can also change the class that they're in. So a few other functions that the administration has is they can, as you can see here, they can see all the users, they can add tests, they can assign teams, and also look at other classes or move them around. So that's really important that the teachers also have more functionality and they also see results differently than the students because the students have it more for them and the teachers have a different way of seeing information. So here are a few frequently asked questions from the project. So what age group is this for? This program is best used with 6th graders and older. So can we edit the teams? Yes, so teachers can edit teams and also set constraints for team assignment like we mentioned before. And also if you want teams from different classes or set multiple teams, we're also working on developing that as well. So can students take the test multiple times? Yeah, so we encourage you to have students take the test multiple times throughout the year to see their growth of the program and see if the calculations are correct. And it also helps us make better team assignments, makes better predictions for those too. So yeah, thank you. My name is Ethan Gotin. I was very honored to be a software developing intern working with Joe and Charlie. And thank you very much for your time. And yeah, thank you.
And I think we have time for questions. We have time for questions, and we'll stop sharing the screen, and A10 will be able to take questions.
I have a question. Is that available somewhere on the platform of education, the EPIC Education Foundation or something like this?
I'm sorry, Eric. Could you repeat that question?
Yeah, the question is that seems to be a very nice tool. Is it available where, how, etc.
No, we're definitely going to make it available. This is one of the tools that we're going to instruct the teachers how to use. We're going to also add to it and improve upon it, because although this is, for instance, uses the temology to cognitive modes as one measure, one of the other things, we have several other surveys that we would like the students to take to make sure that when we have the right teams, when you have the mix of students on the teams, we want to understand what kind of skills they have and at what level, so we make sure they have the optimum chance of success. And then once again, as Eitan said, the teachers could make changes, they can make corrections as they're watching the teams performing as a team.
Yeah, so just like Dr. Kumar said, the teachers can also set constraints, or if they see the teams are not working well together, we can also set another permutation of what some of the most optimal teams would be, which is a great feature. So if students don't work well together, or you see that they're not actually performing properly, we can also make those changes. So yeah.
Another thing, maybe this test, I didn't have time to see all the questions and things, so they're more on the personality and this kind of things. But what about their skills? If we have multidisciplinary students, do we have a way to integrate that? Because in the team, it would be nice to have someone also, it's a restriction, from the social the studies, this guy from biology studies, for mixing up this thing.
Do you understand what I'm saying? Yeah, Eric. No, you're absolutely correct. These are predictions made by a survey, right? But I do not trust surveys per se necessarily. And so absolutely what we want to do is we want to have a platform where educators could actually monitor and analyze the real communication of the students, interaction of the students with material. And that's a whole nother level of research that the Epic Education Foundation is interested in. We'd like to have a platform so we can get thousands of students like Eitan. We can analyze their performance on teams. We could analyze their effectiveness for learning, and we could customize the program accordingly to accelerate learning for individuals and teams. And I think we have a couple of more questions. I see Ada. Do you have a question?
Yes.
So I was wondering, what research is there that establishes whether a person will remain in a personality group for the entirety of their education, and what harm can students receive from being put inside this personality box?
Yeah, so thank you for your question. So this work for temology was also developed at Stanford and also tested on groups of engineers. So it was validated through many different trials. But now what we're trying to do is bring it away from like the college level and also bring it more to students in the Epic Education Foundation, not just middle school students, but also high school students. So we have evidence to prove that it works for college students, but we're also integrating that for the younger age groups.
Okay, and now, Eric, I think Ada has a question.
Sorry, that was my husband asking the question. Thank you for the answer.
Oh, okay.
Thank you.
Excellent.
Any other questions?
Yeah, yes, Eitan, I was wondering, what role does leadership play in the structure that you're trying to set up? For example, think of like if you have a ship, you have a captain so that there's responsibility if something goes wrong on the ship. Even on the small, when you think of a small crew like the Apollo missions, there was still somebody that was the commander of the mission. Is that a good idea to have somebody who directs the group, within the group, I mean?
Yeah, so thank you for your question. So in the inventory questions, we're using the MBTI survey, which also will take into account the students' leadership abilities and other factors to help us make these teams and find which students are have more leadership qualities than others. But yeah, that's definitely something we'll take into account.
Yeah, Eric, the other thing is that, at a young level, we survey the students, we figure out which roles are best suited for these students. But what I would recommend is that the educators, when it comes for leadership, we rotate some of these roles. The other thing is that as we're teaching these students how to work together in teams, the people that we select, let's say they're at undergraduates, and they really believe that they are going to be leaders and they want to go into program management at some point. So we would recommend different sets of lessons that those students that are taking those roles to it can advance. When you saw that picture of the ICED methodology, you saw something that looked like teamwork. And so the person that's the leader of that team, we would want them to take that entire module, right, and complete that module. And we will guide them in their training as they function in that role. For younger students, I would recommend rotating the roles and evaluating the roles and giving those students feedback, okay, so that they learn what a leader is, what a leader of a particular type of team, like the teams that we're trying to create, how they, it's different types of leaders, right? You had a ship's captain, just like we have different types of leaders, let's say flight directors, right? A flight director that is launch and entry, right? You have a very dynamic phase of flight. They have to make split-second decisions. There's no time for having a collaborative type of discussion of what to choose. They have to make changes very quickly. That's a more directive style of leadership, right? And that's a different type of role. You look at all the things that could possibly go wrong, you identify what they are, and you immediately command your people to act a certain way. A flight director that's managing a crew on orbit, totally different leadership skills. And if you mix the two, you run into problems, because on orbit, you have time to try ideas, to test ideas, and to fail, right? And we want that to happen because we want to look for the right solutions to solve these problems. So, it's very complicated, and it's a very short time to talk about teams and high performing teams. That's another book and another course. But what we try to do is show elements of these attributes to students, and we monitor them. And really, we educate the educators to monitor the students on what they're seeing. But like Eric said, we want to collect that information. So once we see those communications, we look at using machine learning, artificial intelligence, which that's the next project Eitan is going to work on with we can understand what's happening so that the machine can guide us and tell us, hey, there's an issue here in this team.
Yeah, so just to add on to Dr. Mara's point, the idea is that we're going to have students be surveyed multiple times throughout the year. So that was one of the points. So in the beginning of the year, we would like the students to be surveyed, and then a few times throughout the year, they could also be surveyed to see and validate our calculations, and also to help us make better predictions for the future to see if it is consistent or if we need to make modifications to some of our algorithms.
Thank you.
Any other questions?
Nothing? Okay.
All right, thank you very much.
Excellent job, Eitan. And we're looking for more interns, by the way. So other students that are out there at all age levels, we have lots of really cool projects to work on. And especially when we start rolling out some of these challenges. Okay, right now we're going to have a presentation by one of our other partners, Siemens Corporation. And we will be using their software for computer-aided design, computer-aided engineering and manufacturing. And so we're giving the educators out there a little bit of a view of some of the tools that we're going to teach the educators to teach the students how to use. And let me see, is Jerry on the line?
I am.
There he is. This is Jerry Gerrans. He's been working for Siemens for a long time. He's a great friend of ours, and he's now one of our partners in the EPIC Challenge program, along with Siemens Corporation. And we're very lucky to have Siemens, and our students and our educators will be able to access their software for free and to use their software in the classroom. And want to thank you and Siemens for that, Jerry. And we're ready for your presentation whenever you could share your screen.
I'm going to attempt this, Charlie. I'm going to go to slideshow mode here.
There you go. We see him.
And okay, so when I go to, let's say, see what happens now. Can you still see the screen?
Yes.
So you don't see the jets, right?
Right.
Cool. All right. So thanks, Charlie. I appreciate coming in, being part of this. I kind of want to set the stage here a little bit. You've seen a lot of things talking about missions and whatever. And, you know, if you look at today's day and world, I'll call it the day in it today, everything's gone digital. All right. And digital really was a preemptor to this thing, or done by things called CAD, CAM, CAE. I'm going to add a new term called PIM. That stands for computer-aided design, computer-aided manufacturing, computer-aided engineering. And PIM stands for Program or Product Information Management. So when you take a look at the way we design things, and again, as you can see by the gray hair, I've been around the block a couple of times. I actually came out of automotive industry back in the 1970s. We were in that time really just starting to toy with computers and doing analysis and whatever. I'm an electrical engineer by background and systems engineer. And the job I had back in the day was actually more of a packaging engineer, where we were taking and doing electrical analysis to help automobiles do their power systems. Again, not like they are today. I mean, software is driven and whatever, but way back in the day, you know, they would throw the car over the fence as an example. The chassis and the body and all that good stuff was part of it. But, you know, it took a long time for people to really get a good idea. We had to wire it and we had to do the electrical, and our backs were always against the wall. Well, we've come way, way far away since that day. And so I'm going to give you a couple of different case studies here to kind of give you an idea of how it's being used today, but how it's mission critical. So the first thing I want to do is kind of give you a little bit of a video on, and I will look for somebody to give me a thumbs up and make sure that the video is playing and you can hear it, okay? So with that, let's get started.
Nothing can be taken for granted when you get to Mars. There's a lot of things we just don't know.
Space always has a way of throwing us curveballs and surprising us.
I mean, until we get the data that says we're on the ground safely, I'm going to be worried that we're not going to make it.
Entry, descent, and landing is often referred to as the 7 minutes of terror, because it takes about 7 minutes to get from the top of the atmosphere of Mars to the ground safely.
The spacecraft has to do all of this by itself.
There are many things that have to go right to get Perseverance onto the ground safely.
There's a lot counting on this. This is the first leg of our sample return relay race. There's a lot of work on the line.
Starting about 10 minutes before atmospheric entry, we get rid of really the spacecraft part of the rover that's been supporting us.
We come screaming in to the Martian atmosphere at 12 to 13,000 miles per hour.
And the heat shield is what dissipates all that initial energy through friction.
The vehicle will continue actually flying itself through the atmosphere. It's sort of like a transforming vehicle that went from a spacecraft, and now it's kind of like an aircraft actively guiding itself.
When we're going slow enough, we deploy a parachute.
It's the biggest supersonic parachute we've ever sent to another planet. It's critical for slowing down the vehicle.
Perseverance's entry, descent, and landing borrows heavily from that of Curiosity.
But fundamentally, Perseverance is a different rover. She's bigger, she has different instruments.
We've added a lot of smarts on the inside to make it more capable so that it can deal with the landing site that we've given.
The science team identified Jezero Crater as basically an ancient lake bed and one of the most promising places to look for evidence of ancient microbial life and to collect samples for future return to Earth. The problem is it's a much more hazardous place to land.
When you look at Jezero, all you see is danger. How do we go to a site that we never thought was safe enough to go to before? So the heat shield, which has protected us all the way through entry, is no longer necessary. We need to get that off so that we can actually see the ground. And we can see the ground in a couple different ways.
Perseverance will be the first mission to use terrain relative navigation. So while it's descending on the parachute, it will actually be taking images of the surface of Mars and determining where to go based on what it sees. This is finally like landing with your eyes open. Having this new technology really allows Perseverance to land in much more challenging terrain than Curiosity or any previous Mars mission could. Amongst the rocks and the craters and the cliffs, these things hazardous to the rover, but these are the things that are interesting to the scientists.
Once Perseverance has figured out where she is, we jettison the back shell and parachute and light up our rockets. Those rockets help us steer to a safe landing spot that's nearby.
That descent stage takes us all the way down to about 20 meters off the ground.
That's when we start the sky crane maneuver. Once the rover has hit the ground, the descent stage will cut loose from the rover and fly away to a safe distance. Surviving that 7 minutes is really just the beginning for Perseverance. Its job, right, being the first leg of sample return, to go look for those signs of past life on Mars. All that can't start until we get Perseverance safely to the ground. And then that's when the real mission begins.
So I tell you that little story just because I still actually have an active NASA badge working out of Marshall Space Center. But while that was a pretty cool thing, you see it in movies, you see a lot of different stuff. The premise, the start of it all came as a 3D CAD model. You know, back in the day, again, not aging myself, but we started with 2D, and then you started at 3D, and now you've got these elements where you've got just building the part. So they talked about the shield, they talked about a number of things. Those are all CAD models that were all put together. But the CAD model doesn't do a whole lot unless you are able to analyze it. There's a best practice out there called analysis leads design. And that analysis leads design means what can you do in a lab to take a look at a virtual element? How can you then make it react on a computer screen? And how can you come up to make something like this happen, like the Curiosity? We've been fortunate as a company to actually work on the last 4 rovers that have gone to Mars. We also work with a lot of other companies, and I'm not here to do any sales to you, but the idea of CAD from a computer-aided perspective, which is digital, then moving into bringing electronics into it, software elements, electrical, which is different than electronics, by the way. There's black box items, there's a lot of different things, but that's the design environment now. So taking it from the life cycle, which begins with CAD and idea, all the way through manufacturing, all the way into making sure it's performing the way it needs to. You know, they joke at NASA, and I'm sure Charlie's mentioned this, you get into space, you can't send a tow truck out to fix it if it breaks. So that movie Apollo 13, by the way, it was real, all right? There were issues. How did they fix it? And you're in space, you're kind of in trouble. So what's the environment today? Well, first of all, around the world, okay, in a lot of different places, the goal of most industry, and I don't mean only space and aerospace, but just about every industry that's out there, is to improve quality of the product, shorten design time to delivery time. Example, when I worked in automotive, okay, our time to market was 7 years. That was the time that we would freeze the design to the time we would build it to bring it out and you saw the new car. And every September, a new car would come out. So we were working on stuff 5, 10 years in advance, believe it or not, back in the 1970s. Kind of hard to believe nowadays. Today, that average is 13 months. So to give you an idea, time to delivery is very critical. There's also a competitive element to that, where a company, Jack Welch from GE used to say it, you get to market a month ahead of the rest of your competition, you'll get 26% of the market, that you'll stay in market longer and make more profit. So everybody and every company's out there needs to do it, but you got to have science, and these kinds of tools are the things that enable them to do it. The last thing is really improving the customer's experience. The customer has to enjoy, they have to get the use out of the product. So Perseverance, which is now on Mars, okay, everybody's heard about that, what they're doing. The experience is really for the government, for JPL and everybody to ensure that it's doing its mission. It's basically a laboratory on wheels, okay? A lot of people think, wow, it's cool, it's a rover. No, it's actually a laboratory. All of the studies, all the things that they're doing are actually being done there on Mars. So basically this all starts, okay? And that's kind of something for students that we're putting together. I am responsible, by the way, for all of the academic enablement or workforce development for Siemens in the Americas for the software group. So I look at things like, how do I start with kids who are kindergarten, who have an adaptability, by the way, and I've got 2 schools that actually have kids that are gifted, that are starting out, but we look through that all the way through higher ed. We also look for innovation institutes. And the key element and the one common denominator is design thinking. How would I build that? So when somebody thought out perseverance, how do they move forward to think about what they do? How do they want the systems to work? The camera system, the arm system, or all of the analysis, which happens to be a part of what they do on that space rover. So basically companies, universities, they really all are moving into CAD world, linking it to CAM, linking it to CAE, also with data management to support it, to collaborate, to do a lot of things is what it's all about. So I'm going to show you another story here. Okay, so it's not just about Mars, it's not just about JPL, but now I wanted to take a look at something that this young lady, her name is Ashley. She had actually done some work with, well, you'll see the story. But the thing I want you to know, she was 15 years old when she started this. So when we talk to high schools and secondary schools and we talk to STEM, I love to show this story because it really starts to bring home what design thinking can be all about. She just graduated, I will tell you that ahead of time, from that school right there, Grissom High School in Madison, Alabama. And she is now working and actually going to school in biomed for her degree at the University of Alabama, Birmingham. And a lot of it was because of what you're going to see here. So this is another short clip. We'll go from there.
I've always been an active person. I've always enjoyed the outdoors. When I was a little kid, the mountain was my playground. It's always going to be a passion for me. I was an infantry assaultman in the Marine Corps. I was shot in Afghanistan in 2012. Those injuries left me partially paralyzed, and I decided to electively amputate my leg. I have a pretty heavy-duty foot. It allows me to be very active, but at the same time, it's a bit heavy. Anything that requires more energy really just fatigues me faster.
I live in a nerd town. Huntsville is the hub of engineering in Alabama. We have so many new career tech programs like advanced manufacturing and engineering right in our high school.
Reset the clamp, a little bit tighter. My brother started a school initiative for engineering, and he had a student who was really interested in doing some kind of biomedical project. Well, maybe she could redesign a lighter, more versatile foot.
So this is the mold, and we printed one of these. I'd always kind of wanted to be a doctor. When I discovered biomedical engineering, I was like, well, that's the perfect combination of medical and engineering. The whole foot together weighs 2.5 pounds. Ideally, we would like to get it within 1.7 pounds.
Yeah, that sounds great.
Once we got the prosthetic from Kendall, we had crazy ideas. We took the whole foot apart and modeled the original prosthetic in Siemens software. And I'm just gonna draw 2 holes there real fast. Solid Edge lets me design and test the foot before we ever actually build it. We tell it a few things that we need, and then it takes all that information and it decides what's going to maximize the strength and minimize the weight to create a part that would be the lowest weight possible for Kendall. This has taken almost a year to the day. I don't think this has ever been done by a 17-year-old girl before. There you go.
Awesome. It feels strong, it feels sturdy. It does feel a lot lighter.
Nerds rule the world. Nerds got us to the moon. Nerds are doing things with prosthetics that I have never dreamed of doing. And go.
Having a lighter foot is going to open up possibilities that would not have been there before. You know, the more kids that can learn this stuff at earlier ages, they can go on to create new and better things that we're not even dreaming of right now. It's amazing.
In the future, I want to do the things that are impossible right now. If I can design this prosthetic now, I can't wait to see what I will design in the future.
So as a side note, I presented that to the high school system in Camden, New Jersey, not long ago. And it was just something that, you know, these high school kids in an inner city really took hold of. And the whole idea of STEM, the whole idea of, again, moving in some of like the EPIC Foundation and things like that are just absolutely cool. One of the reasons we're so geeked about doing it. A couple things that I want to kind of mention here in a quick summary. You know, when you think about design thinking and you think about CAD, CAM, CAE, it's now expected. It's something that years ago was a nice to have. When I first got in the industry many years ago, when I was an engineer, you know, I've been on the software side of it really as a supplier for now a lot of time, long time. But the idea is now it's not just the mechanical part anymore. It's the systems part of it. So when you start to go into design thinking, you think about, again, how things are made. But secondly, also now chemistry, you think about how things are made, you think what they're made of, materials management, okay? You look at Kevlar, you look at lightweight, you look at a lot of things that, you know, a bulletproof vest or a enclosure for a racing car is an example. A lot of stuff that's going on, but you know, the brain and bringing it apart, and both Kendall and Ashley made a great point, okay? You really want to think about what's possible, all right? And what do you do? So another thing that's really important, okay, to us is how do they fit together? So the ideation, we kind of put this thing into what you'll hear a term called digital twin. Digital twin is basically the virtualization of a real product, but it's good to design it, which you see here. Ideation, CAD, and computer-aided engineering. You'll hear the term modeling simulation. That's really cool. What you saw with Perseverance was a lot of modeling simulation, okay? Can it happen? You know, there was a mistake by NASA many years ago. Okay, we won't talk about it, but it was an English versus metric calculation that had a little bit of a breakdown. So now you can simulate that and do everything on a screen prior to watching it happen. When I actually worked in automotive, we used to take our cars out to the test track and they'd crash them. Then we'd look at them and figure out what went wrong, what was the weakest link. Now they can do that all inside of a computer. But the key behind all this is really looking at how do you connect it. So you've got ideation, which is the design part of it. Can I build it? Okay. So what is it going to take to do that? You know, we ran our harnesses and we would run it through the body. We'd have to do work to create holes, okay, to put our clips and different things in. Believe it or not, that was a major engineering thing because it weakened the structure. And if you then had a crash at 45 miles an hour, did it kill somebody? So it sounds like, wow, just a little hole. It was a big deal, okay? But then there's the last part of it. Does it, oh, sorry, a little quick. The utilization part, is it meeting the requirement? So when you saw the Perseverance demo, you really saw when it was landing and when it was ready to go. Did it hit the mark when it needed to go? I like to kid around with academia, professors and whatever I deal with a lot. And I say, well, you know that Ferrari you're driving because of all the great stuff you get paid for at that university, is it really doing 150 miles an hour? So who knows? You can advertise all day long, or a printed circuit board, or like Siemens, there's another part I pulled out of it. We're into the wind energy piece of it, right? Those blades, okay, are designed to last 20 years. Are they? Okay. So there's a lot of things that now, are you getting and planning and are you engineering into the product, all of the things it can do? All right. So that's kind of where CAD, CAE, PIM, how do you manage today to collaborate, all comes in together. We believe innovation is the key to it. You start off with an idea, but how do you make it real? Secondly, we're looking at it huge from an academic focus. And that's really how Charlie and I have been talking now for a while and what we're doing to provide the software. Ashley showed you a demo of the Solid Edge product. We've got a lot of other software. In fact, our price book's about that thick. All of that's available to the foundation. Shaping the future, research is key, okay? This is where things like Perseverance come into play. Sure, they built a product, but they had to research and they had to do all materials manage, all the things we're talking about. And basically, finally, enabling the future through design thinking, trying to get out to these kids, okay? Getting them to think out of the box, think about what if. You know, there was a commercial years ago by, I think it was HP, that said, what's possible and what if, right? And the thing is, that holds so true today and as we continue to go forward. So I want to thank you for your time. Charlie, hope I was on time for you guys and looking forward to any interaction and helping you out.
Jerry, Jerry, that was perfect. You're spot on. We're ahead of schedule. And we have a question from one of our educators at Bergen Academy, Eric Paul.
Hello, it's such a pleasure to hear this description of how students should can utilize this. So, how do you what's the best way for students to learn the CAD? How can they learn it on their own? Or I realize we have classes where we do that, but what if a student wants to learn it on their own?
So that's a great question. So we provide a tool called Learning Advantage. Whenever we engage with a school, we do a couple things. We give a grant with Charlie. And so the software is available, but there's also an entitlement that comes with that grant. And that's access to a database for two people, well, two schools, faculty and the students themselves. So they're able to go download the software for free. There's self-taught tutorials. They can learn it on their own. During the pandemic, a lot of students, college and some of the other schools, use this to their advantage because the kids were stuck at home. So they actually built a lot of their lessons on Learning Advantage, what they did, and then they would test out. We also certify, our products. So as a student goes through and learns and goes through a testing element before they get their degree, a lot of companies still regard they need a 4-year degree, but badging has become important. Certifications have become important. So we also offer a lot of that. But we offer another last thing I'll mention, and that is thought leadership, and coaching. So we want, and we don't want to step on the toes of the education system, meaning the teachers and the faculty and the people that are doing it. But if there's a kid, that wants to learn, is looking for something, like Ashley as an example, we have a team of people that are support, and we do, my organization, give support to them direct. Does that help?
Thank you. Thank you very much, Chair.
That's excellent. Are there any more questions? That's a great answer, Jerry, and it's good to hear that you're offering support and we have a learning and tutorial capability go along with that package. That's critical. Any other questions in the audience?
There's a hand up over there, Eric Romer.
Yeah, it's not really a question, it's more a comment. In 2015, just to link with Copelia Sim, which is also known as VREP. I don't know, Jerry, if you, Gary, sorry, if you know about that, but in probably not. I mean, Siemens is a big industry, but there was a joint workshop between Copelia and Siemens in 2015 in Tel Aviv, where they actually built. I'm going to read the statement. Steam and Energy Software and Copelia Robotics held a joint workshop to explore possible synergies between Process Simulate and VREP. At the time it was called VREP, now it's Copelia Sim. During the workshop, this demonstrator was created. Just to show that there is already an interaction with Siemens and the simulation, the simulator we are using for this course going on. So there was something. I don't really know how. What was the consequences with that? I can ask Mark, the director of the CEO of Copelia Robotics, but I remember that he was mentioning that there was this interaction with Siemens, and mostly when he explained me what happened there, he said like, "Wow, those guys." That was that.
So it's interesting that you bring that up. So I talk and represent, we call it digital industry software, under Siemens. We're under the digital industries umbrella, which is under Siemens AG. As many of you may or may not know, we're about 400,000 people strong. We've got 6 different business units that play in all kinds of different things. And what's happening in something I work with on a regular basis is synergy with them. So we do hackathons as an example. And we do projects like that and with companies, and there's just stuff like that all over the map. So I guess the other thing, design thinking, I'll bring it back. Don't just put yourself into the mind of building a product. For example, we as a company have always focused on the product. So when you saw Perseverance or you saw the foot, that's the product. But if you take a look at a plant, or where some of you are sitting at Kennedy Space Center, there's an environment. So we have a group called Smart Infrastructures. They think about when you walk into the room, how do you do the air conditioning? How do you do the alarm systems? How do you do all that? And that's another learning environment, right? So not only do you build the assembly line through our factory automation and things Siemens does, but you also have the facility in the building. Well, if you take a look, and some of you are in Florida, if you are on the Orlando Turnpike, or the Florida Turnpike, and or around Tampa, you'll find that you have these lights that go on that stream the cars on and off. Well, ironically, behind the scenes is one of our products called MindSphere. It's our IoT product, but it actually manages the traffic system through our mobility group. So that just gives you an idea that, if you're looking at solving a problem, don't just stop and say, oh my God, I have an inhibitor, but what's possible? And Eric, to your point, when you get into robotics, we, by the way, sponsor First Robotics for those that are familiar with that. It's based out of Boston. But that's schools all over the world, actually. And that's kids, middle school kids, high school kids, that are building robots. And, MIT, I think, started all that when they had that battle of the bots and whatever it was. Well, now it's gone viral. And a lot of that's all done. So we partner with a lot of software people that do that too. So, but thanks for the comment. Appreciate it.
Okay, any other questions for Jerry? All right, Jerry, I want to thank you again. It was a great presentation. It was wonderful stories, very compelling stories. And sometimes it's not just the technical part that attracts people to engineering, but it's the social element, doing something, giving something back for society. Thank you, Jerry, and we'll have lots to talk about in the coming weeks.
Absolutely. Thanks, Charlie, and thanks, everybody. Appreciate it.
See ya.
Bye-bye.
Okay, so where are we? It's 12:50. We have time. Anna, should we go to the next speaker, or would we like to do something with our teams? Okay. Let's see. Do we have our next speaker is going to be Daniel Nelson. Daniel, are you with us?
Hey, Charlie, how are you?
Hey, how you doing? Hey, I met Daniel in New York at a Google conference, at a Google meeting, and he was this amazing young entrepreneur that started a new company called Grow Computer, and he now has a nonprofit called One Grow. And the beautiful thing about his program, his company, and also his nonprofit, it merges nicely what we're doing at the Epic Education Foundation, the Epic Challenge program. And so one of our challenges, our sub-challenges of our main challenges, sustaining humans on the moon and Mars. And how do we do that? We need to grow our own, right? You heard a lot about in situ resource utilization. Well, Daniel is going to talk a little bit about his company, the vision on where he sees his company going, his product going, but also how that impacts education and his nonprofit. And so, Daniel, whenever you're ready, I think we have extra time, Daniel, so don't feel like you're rushed, okay?
That's great. Thank you so much for having me. We had tried to produce a quick video, but unfortunately, technical difficulties. And also, after following some of the amazing production videos that we've seen this weekend, it's probably for the best that our homemade video didn't quite connect. But once again, thank you to Charlie and Joe for having us today. It's a real honor to be able to participate in such a cool project. And as Charlie mentioned, we met, I guess, 2 years ago at the 50th anniversary of the moon landing event that Google had hosted in New York City. And I think we just happened to meet at the cocktail hour afterwards, and I had a chance to explain some of the things that we were trying to do at Grow Computer and some of the really interesting and exciting findings that we learned. And so through my time at Grow Computer, I am not in the IoT space or the ag tech space by definition. In fact, I am a recovering accountant. And I actually think that I've been on an odyssey through this space for a long time to create our company, Grow Computer. Because as we talk to people that are doing this and hydroponic farms and growers around the world, one of the things that became so exciting is that teachers are using these systems in classrooms everywhere. And they come in all shapes and forms. Just from my building Grow Computer to talk about delivering better digital tools to growers, we learned that teachers are using these systems in their classrooms everywhere, but they had no digital access to these systems when they weren't there. One interesting story was if your teacher was locked out on vacation, they had a false positive reading that a water pump was on. They had to run all the way up. They had to run in the New York City subway for an hour and a half to go up there. But all of these different farms that we learned about came up to one really interesting question. And it's ultimately, how do educators around the world use hydroponics in their classrooms? And this is a fascinating question. And I had been asking it for a few years and nothing really mattered. Sorry, I'm bouncing around a bit. Until last year, just before the pandemic, I was offered an opportunity to go back to my alma mater, the University of Michigan, and talk about what we're building at Grow Computer. little did I know that in the audience that day were some students that were part of the Net Impact group at the University of Michigan. For those of you that have heard, Net Impact is an international organization where college students work with entrepreneurs and startups to help them deliver the solutions. And together with that question of how do teachers use hydroponics in their classrooms, plus the access to the talent, resources, and energy of the students from Net Impact, we were able to create One Grow. And the first thing that we learned that really excited us, that absolutely connected us to Charlie and Joe and the Epic Education Foundation, is that the really exciting thing was that hydroponics is cool, right? It's cool to grow food. But what's more important is that hydroponics is a vehicle that teachers and educators are using to build multidisciplinary learning teams to solve a specific problem. Anybody, just like everything else that we do on a daily basis, you can't just take one skill set or knowledge base to solve these challenges. Every single thing that goes into these systems is almost its own science. And we've seen how teachers are able to combine software engineers and systems engineers with agronomists and nutrition experts, with an entrepreneur and a marketing resource to build little businesses and to learn how to put these different skill sets together to deliver solutions. And so last year, we wrote a series of grants called Deep HydroSense. As every good grant needs, we had a fantastic acronym. And the acronym was for Distributed Experiential Education Program Using Hydroponics and Sensors. Basically, the idea was that we were going to invest in a deployment of software of IoT sensors at 4 different high school classroom farms in the United States. 1 in California, 2 in Pennsylvania, and a couple in New York City. And we were going to actually see if we can get these students competing against each other to grow better food, or use the least amount of energy, and come up with a lot of different types of collaboration, as Charlie introduced us to. And so ultimately we didn't get it. We were unsuccessful in our grants with the USDA, but luckily we had a lot of great energy and momentum, and we didn't want to let that stop. And so what we've done is we turned all of that into onegrow.org. And onegrow.org, at least in our goal, is to be a digital platform of resources that is free and publicly available to any student, educator, public representative, or nonprofit affiliate. And so as we look at what the long-term value of what we can deliver is, the first thing that's really cool is, since I am not from this space at all, over the course of my career, journey into this world, I started aggregating and collecting and curating articles, videos, scientific studies, infographics, curriculum, DIY plans, other plans, even GitHub links for open source software. And I started just aggregating it into what was then a Google Doc, basically. And so this asset was just sitting there. We have a couple hundred subscribers to it as it is. It's free on the internet. But we said, what if we take this asset and make it into onegrow.org? And so that is what we are launching, or we're delivering the next step of today. And so what this place is going to be, onegrow.org, is a free and publicly available set of resources, and curriculum and challenges eventually, and whatever else that we could put in here to talk about these industries of the future, to help teach students about all of these exciting sciences, developments, and opportunities. A lot of the stuff that we spoke about today, we are working on kind of integrating into that, because all of this content to us is connected to everything else. It is not just learning about hydroponic science at once. It's about learning how hydroponic science in the first step can lead a student or a person down a pathway to really explore and investigate these exciting opportunities more fully. And so it's live today. Our brand new website, it looks totally new. It is onegrow.org. It is our V2. And we're very excited about where this future will take us. Please sign up and let us know if you have any access or resources or people interested. This is designed to be free. It is designed to be for people. And we believe that if we could do our jobs well by creating a great platform, collecting the best content, and connecting with the smartest people, that ultimately we can go back to that original vision of the global hydroponics collaboration. Because if we can connect people with the assets that our team has now, and we can create exciting experiences, over time, we believe that we'll be able to essentially stand up these open source, massively open competitions. And originally it was called the X Prize for hydroponics in a classroom. Charlie and I have started thinking about how we can work together with the EPIC Foundation to help sponsor some of these exciting challenges. But if we're saying that any indoor farm is really just an artificial environment, by definition, those could be anywhere, whether in a classroom, whether at the Mars Research Station or the Johnson Space Center, or on the moon. And so what we're trying to do is to connect those spaces together to allow students and teachers to learn from each other as much as building it themselves. And we are very excited about where this is going to take us. Once again, thank you to Charles and Joe for all of the support. Joe has spent so much time with us, helping us to figure out how to develop this platform in a really scalable way. And we are excited about where the next year is going to lead us, because we've seen such an exciting boom in hydroponics in use of education. So that's all I have today. Charlie, thank you so much for welcoming me into the conference, and I'll pass it back. Or if anyone has any questions, I'd love to answer whatever you guys have.
This is awesome, Dan. And there are so many really cool epic challenges, and we've been focusing on space, and naturally we think that's really cool, and it puts you in that extreme environment, so you're testing all your knowledge and all your assumptions when you're growing things here on Earth. But it also helps us develop new technology, and you're working with that technology right now. And so yeah, we're going to try to grow food in space, but we can't have the astronauts on the moon and Mars be farmers, and that's all they're doing, because there's so much more. So how do you do this automatically? How do you do this autonomously? And those are the challenges that will help us back here on Earth. And so now, if we have any questions for Dan, if you will raise your hand and we can see you.
Eric.
Here we go. Who's that?
Me again. In Brazil, there is a huge. Is it okay? Can you hear me? Good.
Yep.
So in Brazil, there is a huge investment in precision agriculture. So of course, it's not precision agriculture. If you hear that, you're talking about like big fields and trying to deal with that. So the automation of that is another scale. It's something else. But there are a lot of projects that are actually working, and I'm working actually with Embrapa, which is an institution doing a lot of research, and famous one in Brazil and in the world, and where they are focusing on this kind of, for instance, the project I'm working on with Embrapa is to find some using machine learning to define the quantity of and the quality of raisin while in the big field. So there are like, I guess there is some spot to have like automation of this kind of things, like counting, surveilling, monitoring, even eventually collecting the fruits or the vegetables. I've seen the design of a little robot getting out of one of your slides, and I thought that this is the kind of things that that you guys are doing or willing to do. Eventually, there's a possibility. If you, as I have like good results in Embrapa, maybe I can connect you with, or I will connect them to you. I will tell them about that, and maybe something good can happen. Charlie was oh no, you were actually commenting that everything is happening in a conference when there is an event, while when there's the social event and people drinking and eating and conversing, networking together. So that might be the result of that right now.
Eric, thank you so much for that great question. Yes, and what's actually cool is that in Brazil, Charlie pointed me in the direction of some research that's happening at the Federal University of Rio Grande do Norte. And what's cool is they've actually built in the desert, about 2 hours from their campus, something called Habitat Marte. And I had a chance to connect with the researchers last week. I feel like this audience would be really excited about this. But they're building a controlled environment farm in an extremely remote environment. And so for us, we would love to be able to connect this in. It's a very cool project. But why we think that this is a really exciting approach is that when you think about a plant, there's only really 10 to 15 major data points that are that govern a lot of the growing and farming that go in there. And so in a controlled environment, we're bringing those into a artificial place, but the same seed can grow outside in the same way. And so we think the controlled environment's a little bit easier to manage because it's totally within the classroom. But those same principles about understanding the environment to then be able to augment it and deliver additional resources, nutrients, energy, water, whatever the plant may need to optimize it, that's universal. And so these skill sets of understanding these systems and how inputs and sensor data can work with automation and other types of actuators, that's universal. And so we're hoping that this first step, as we're able to connect to more and more and more growers around the world, we could actually start to see it and maybe do an A/B test of indoors versus outdoors and see if we could tune an indoor environment to match an outdoor, to then be able to see the learnings that we can garner from them. That's the vision. That's the long-term goal. And thank you for your great question, because we are absolutely looking to do that. And I hope that we can work together going forward.
Thank you. Thank you, Daniel.
Eric Paul.
And just wondering, is this something? What are the kinds of scales involved, Daniel? I mean, for example, I think I've heard that there's talk of putting you could put something like this in a skyscraper. Is that true?
Yes, theoretically, yes. I think the challenge is, and I have a lot of thoughts that might be counter to a lot of what you'll hear in ag tech speeches, but I think ag tech, at the end of the day, any of this controlled environment farming is really just an energy conversion. And so when you're doing it indoors, you're converting electricity in the form of watts into calories in the form of food. And when you're growing things like lettuce, it's very effective because you're harvesting almost 100% of the biomass that you're converting it into. But when you're looking at something like tomatoes, you're actually only harvesting a marginal percentage of the overall biomass that you need to grow. And so the total amount of costs that go into any of these systems can be prohibitive from doing them in something like a skyscraper. However, at the same time, if you're able to do something like a smart greenhouse where you're able to use the fusion reactor in the sky and then augment the rest of the environments, now you could put a greenhouse on top of a skyscraper and get some local produce. And I think it's, there's a lot that the space needs to learn about the functionality and actual viability of these urban vertical farms. But I think where we're going to end up is that the technology that's been developed in vertical farming, a lot of which was used for other sort of we'll call them more medicinal plants in the United States, that market has driven the innovation into the space to drive down the costs of the lights and the pumps and the sensors. And so as those keep coming down, the cost per pound of any crop comes down. And so you'll see that there's going to be a market clearing price for any of these crops in any local market. And the challenge is for the entrepreneur to figure that out. And I think but for an educational purpose where the goal isn't necessarily to drive economic returns into a local business, teaching students through this lens is a really great way to teach about food policy, to teach about electricity, to teach about systems design and project management and interdisciplinary sciences. And so it's been really successful. And then not to mention that in North America specifically, the school year was designed to be antithetical to the growing year. So 90% of teachers in the United States can't plant a seed in September and teach their students about that plant over the course of the calendar year because that's how the school year was designed. And so there's a lot of these things where, because it doesn't have to be economically viable, you're able to do a lot of really exciting development in education specifically.
Wonderful. Thank you very much.
Excellent. Do we have any other questions? Okay, it looks like we have time for a break. I think it's time to take a 15-minute break. Maybe we'll come back at 1:30. We have one more presentation by James Gorman and Brian Moon on the idea of using concept mapping, not only as a tool to teach, but also to compartmentalize knowledge, pull it all together to help us solve multidisciplinary problems. So we'll take a break for 15, 20 minutes. We'll come back, we'll listen to the last presentation, and then we'll have, if there are any teams out there that would like to demonstrate their solutions to the problem, we have Andrew here. He'd be willing to run your simulation. Run the actual code. I'm sorry, I said simulation. I meant the actual code on the real robot right here at Kennedy Space Center. So we'll come back in about 20 minutes at 1:30. Thank you. James, I am so sorry.
No worries.
We were delayed by 6 minutes because I was playing with the robot over here because we really want to beat you guys from Bergen Academy. I see Mike Lever's up there. He's probably in the laboratory working on it right now, Mike, right?
Yeah, we got a bunch of ideas.
You got a few ideas, Mike? All right.
Yeah.
Okay, we have our next presentation today is by one of our, I guess it's our longest running educator that's been with the ICED methodology and the EPIC Challenge program, Mr. James Gorman at Nipmuc High School in Massachusetts. And together with Brian Moon, with his company called Zero Learn, we're going to talk a little bit about concept mapping. Okay, so concept mapping is a phenomenal tool that our educators use to help students learn and to help them gain knowledge and to construct knowledge. So James, Jim, and Brian, whenever you guys are ready to go ahead and share the screen and begin your presentation.
Okay, I think you can see my screen now. Let me know if you can't. Of course.
We could see it, Jim.
Perfect. Excellent. I'm just trying to get this up here. Okay. Excellent. So I'm here to talk to you about 10 minutes or so about concept mapping in general, how we kind of use it in the ICE methodology. And then I'm going to turn it over to Brian Moon, who's going to show you an even more powerful way of harvesting what we're doing with concept mapping. He's been developing with this with the US military. So I'll leave that to him, and let's go over what concept mapping is. So my part of the presentation is in a program called CMAP Tools, which is built specifically for making concept maps. It's online. It's also free to download. It was also developed with US military funds, coincidentally. So talks mostly based off of my work that I've done with Bloom's taxonomy, as well as chapter I wrote for a book about how concept mapping can be used to change the way we do science education, shift it to more of a meaningful learning, critical thinking mode. And so the form of this presentation is in concept map form, right? So a concept map is essentially a bunch of concepts. So these are the bubbles you see here that will pop up. And they're linked. And different from mind map, right? Mind map's link, but there's no description of the link. So it's kind of a fuzzy relationship, right? The map's telling you there's some relationship between those two concepts, but a concept map in particular is going to define that relationship between the two concepts. So in essence here, you could read these as sentences, or we call them propositions. So they're true statements. So concept mapping for learning session will engage students with, that's the linking phrase, concept mapping, right? And these here, this is particular to CMAP tools. You can attach things to it. And this map here will actually take you to a whole nitty gritty on concept mapping, who developed Joe Novak, Ossobillion. It's built on top of Ossobillion thinking, Piaget, all that great educational psychology that we don't have time to go into today, but it's there. I'll provide the link in the chat for you so you can come look at this map, delve deep into it. My contact information is here. Feel free to reach out. Seniors are leaving this week, so I get more time now. So yeah, concept mapping falls into a broader range of conceptual. Yeah.
Jim, you have more than 10 minutes. You could take more time. We will have a lot of extra time. We don't have as many teams demonstrating their results at the end of the session. So don't feel rushed, okay?
All right. Well, Brian has a lot he wants to show. So,
okay,
I'll go through this, and, people have questions, please feel free to unmute, ask me. We can delve into it. That's fine. Yeah, so concept maps, broader range of conceptual maps, right? We talked about mind maps, but, I developed a thing called strand maps, which we developed for the state of Massachusetts to look at and redesign, actually analyze, and then redesign the whole K through 12 curriculum here in Massachusetts for STEM. So I focused on physics, chemistry, and engineering, and my partner focused on the biology and earth science. That's what she did. Yep. Those two. I mean, we could delve into it a little bit, I guess. Oh, it's not coming up very nicely. Essentially, it just shows the span over time. I can talk more about that at some other point, but essentially, we're all about meaningful learning, right? And conceptual maps kind of fall, or it's a big category, let's say that, right? But they're all designed and they're facilitating critical thinking. They each have their own advantages and disadvantages depending what you're doing. Just like bullet points, numbering schemes, right? Those are great for some applications, but fall short on others. It's across the spectrum here. Okay, so returning back here, we have critical thinking, all designed for meaningful learning. And really what we're focused on here is the conceptual change. That's what we want to notice in the students, track, and be able to hone in on those misconceptions. That's where I really find the power of concept mapping, because it makes their internal thinking visible to me and the other students. And then we actually get to negotiate the meaning of things together and arrive at a more deeper understanding of it in particular. Okay. So, right, conceptual change. I don't like this. Let's go back. I thought I loaded it. Hold on, I'm trying to find, oh, maybe I put it up here. Sorry, I'm trying to find my example I put in here of conceptual change, but task system. Oh yeah, these can be done on whiteboards, right? Simple little whiteboard type stuff that don't have to be done on the computer. So you see here, we were just doing scalar and vectors in physics. And so they're given a bunch of terms they can use, like quantity, scalar, vector, units, magnitude, and then they're tasked as a group to come up with a way of linking these all together so that it makes some sense. And so this is just an example of that. But where did I put mine? Yeah, negotiate meaning, right? These are all the Bloom's taxonomy, the higher ordered thinking. That's really where concept mapping excels. Analyzing, evaluating. Wish I had. So usually, if I'm going to start something, I usually start it with sort of a skeleton map view. There's different ways of doing this, and we have more time over the summer in a longer session. We can go over the particulars of how you run different things, and probably Brian will show you how to set it up in these types of assessments in Cero. But in general, expert skeleton maps, you just kind of set out for like a unit, let's say. You set out all your concepts, you link them, This is your understanding as a master of the topic. And you're expecting your students to kind of come close or innovate. Good grief, that'd be great if they could innovate, but at least imitate your thinking, right, as a master. And so you're looking at that, scaffolding, the learning, all these keywords we always use. But where did, hold on a second. All right. We are going to, there's a good example of a student's conceptual change I want to show you because I think it's important here. Of course, it's not going to. Get to see the behind the scenes here. Classroom level, here we go. So this is a series of snapshots of students. This is actually a physics class. These are old. Don't know why it's taking so long. Here we go. So this is their first attempt after I gave them, I would have given them this top part, kind of scaffolded it, talking about motion. There's some relationship, right? Curves in space and time. There's these three main concepts: velocity, acceleration, displacement. And then all of these concepts over here and the one dimension, these would have been listed over here on the side, along with the focus question, which is really what the student's trying to display their understanding of. So in this case, it's how can motion be described or represented? And so, right, for the unit, they don't know very much, not surprising. But as the unit goes on, they're able to start adding more concepts to it. Sorry, my timer. Add more concepts to it and make it more elaborate. They make it their own, right? And then, we're working on untangling these concepts. So now you can start seeing it's gone from kind of a mess, not knowing what goes where, to, oh, look, I have some lines going down here. So I know there's something about displacement. He knows there's something about acceleration. We know about velocity, but there's no relationship between them shown here, right? Along with these two, we can put them in a graph, shows position, that type of stuff, but right? Then you end up with really a map like this, which ends up into more of a network structure. So now when I look at this, I'm like, now I can see the student is starting to really understand the concepts and the relationships between them, because now I have some relationship between velocity and acceleration, right? Still struggling with relating displacement to everything. And then I can, well, this is CMAP tools I took a picture of, so I could even leave notes for the students in here on, think about this, what about that? And yeah, you'd spend time analyzing this. It's quite interesting what they get. They get into these whole networks, everything's sort of related here, which is exactly, and then this is more of their final version. So we can see their change over time. That's really what we're looking at with concept maps here. In terms of ICE methodology, where do we find it? Well, I usually start off the whole challenge with a challenge description. Okay, so here's the description here, written out with links. This was the pandemic proof world epic challenge from this year. But then I also give them a concept map view. right? So we kind of link it. I make kind of a concept map, not exactly of what's above. This is kind of an overview of the pandemic as a whole. And then I link to the map. There's a better version of it. So we can talk about the different aspects, how they're interrelated, right? So the pandemic has many different aspects: telemedicine, shifting resources, PPE, there's virology, there's epidemiology, there's testing, there's symptoms, right? Medications, all of this goes into the pandemic proof challenge. So I want them to kind of see the big picture of what is happening here. And then we can kind of zoom in on particular topics. Someone might really be interested in AP biology. So epidemiology, virology stands out to them. And others are more on the hands-on thing. So they're over here trying to develop stuff that they could use, okay? More practical stuff. And then I also, go away, functional decompositions, right? So I think you had a session on this earlier. Kind of use this to make the aspects specific. So this is, again, the pandemic proof challenge, right? This is just an image of it. You can't click on anything here, but I provide the link down here to the specific CMAP. And so then we look at it in terms of functional decomposition, right? We have all those other aspects, but really what's going on here, right? You could study the origins. There's the stages of the stages of management. There's public health, supply chains, economy, mental health, all sorts of things you can go into, but it just provides them a nice kind of like flow chart view, but also describes things. And I use CMAP tools, so I'm able to attach links to resources I want them to look at. Might be websites, could be papers themselves, all sorts of stuff to direct them. But also, you could do this in a bullet point. I also provide it that way, so they could make notes underneath each one, what they're interested in. So there's two different ways of viewing it. Me, I prefer this. It's visually more stimulating. I can kind of see the relationship, but those are two different aspects there of it. And I've gone over on my time. So I'm going to switch to Brian, who's developed CeroLearn, which is a concept mapping assessment tool. So in the concept mapping community, we've struggled for years to, how do you assess these maps, right? Because we're used to bubble it in, right? A, B, C, D, E, what's the right answer? Well, Brian's been working with the US military to solve that problem. So Brian, you there?
I am. Great. Thanks, Jim. Appreciate the lead in to say we've solved the problem. We are in the process of solving the problem. But
much closer than we were.
Great. Yeah, fair enough. So thanks, Jim, and thanks, Charlie and Joe and everybody else who's gotten us involved in the program. I'm going to go ahead and share my screen. And what I want to do is just give a couple words up front about our program, not only Cero as a software program, but sort of where we've come from, where we're going. And I'll be referring back to Jim's presentation because he made a couple of key points that are really relevant to where we're at. So we've been actually at this, as Jim said, for a while. We've had a series of R&D grants from the U.S. intelligence community actually to start, and then the Department of Defense thereafter. We actually started this whole process. If you think about a concept map and those kind of links between that create those relations, you could also think about people coming up with their own relations, right? How do these concepts relate? So we actually started out, Sarah, in 2014, developing a game where we would just give people 6 random concepts and have them try to tie them together to make a joke or tell a story, that sort of thing. And so that code base allowed us our next starting project. This was with the Department of Defense's Advanced Distributed Learning Initiative. Folks might be familiar with things like XAPI to enable learning tools to share data with one another. We were in the Total Learning Architecture program in order to build out our first version of Sero, but also to share Sero data with other learning tools. And so that took us another stage. We then got funded by the Air Force, who for years had done some work in trying to form teams by comparing mental models of each teammate. And so the work that we've been doing is to use these concept maps as Jim said, externalization of a mental model. How does someone think things fit together, and how do they think they work? And so that can allow us then, if we kind of have a sense of each person's mental model, to sort of form our teams around whether they're similar or different. Our next project, then, we're currently wrapping up our Air Force project. We're also doing an Army Research Institute project. Their call was, how do we automate the authoring process for assessments? And so their actual question was, how do we automate the writing of multiple choice or true false questions? We went back to them and said, we think we can actually get pretty far in automation and authoring, but we'd like to do it with these concept maps, and they got interested in that. So where we're at now is working on these projects and then advancing Sero, which is our learning assessment tool. What Sero does, and I want to draw attention again back to Jim's point about those expert maps. We actually take the expert maps and we have 2 approaches for turning them into an assessment. So the first assessment, we actually call a skeleton map as well. And so the idea here is, if you start with that expert map, but you hide some of the content, and then give students a variety of ways to complete or edit or correct misconceptions within the map or add new content to it, they get that scaffolding, as Jim noted, of some of the expert knowledge, but you get to see where they may have gaps, where they may still have misconceptions, and kind of what their ideas are about what this map should look like. So Jim sort of noted the imitation of the expert, right? The master map. That's what we're trying to do with these skeleton maps. What's nice about these is that the original map itself, that expert map, can come from the instructor, from the teacher, right? So now we're not reliant on whatever our item banks are that come with the textbook tools that we use. We can mix and match these things. We can create maps that are cross-disciplinary and touch on a lot of different varieties, aspects of a given problem, instead of just being sort of narrowly focused on a given topic. So these maps, as Jim noted, they can literally say anything, right? They can make declarative factual statements. They can show reasoning, and again, because the semantics of the map, that is the concepts you choose and the linking phrases you make to connect those, they can say anything. And so we've seen maps developed across all topics in lots of different languages and at all levels of learning. So we know that those master maps can really be reflective of knowledge. Another approach that we have is to say, okay, if we have that master map and we just give everybody the concepts and the linking phrases, what does it look like when they try to assemble it? Right. And so Jim's conceptual change maps were really nice, because you could sort of see over time, as he noted, those maps getting bigger, more connections being made. What we're doing here with this build-a-map approach is, if we give everybody the same set of Legos, what do they build out of it? Right. And while there is that underlying master map of how these things should fit together, we can then compare. We can compare students to that master map. We can compare students to each other. And so this gives us a nice way of, again, taking the structure away, but still having them wrestle with those propositions. How do I state these propositions? Which way are these concepts connected? And so an overarching message that we're trying to get across here is Jim's examples were great, and they're what we'd like everybody to be doing, right? But I'm sure Jim will also note how much time and care he's put into his concept mapping approach. And then, for each map that a student creates, that's Jim going in and adding those notes. And so we're also trying to get some scalability with this approach, so we can have students go through concept mapping exercises that get some of that same value, but that also scale across larger groups of students. So efficiency is a big deal for us. Scalability is another big deal, but we're still trying to stay within, those fundamental benefits, as Jim noted, for what concept mapping can do. We can show that change. We can show comparisons across people and across time. So that's what we're after with these two approaches. Just a couple of notes here on some things that we're working on. As I mentioned, our Army project is about automating the authoring piece. So as we've said, that upfront piece about creating that master map, we're using some AI, natural language processing tools to get that initial map out of things like text. So you're not necessarily hand creating these maps from scratch every time. We're working with the University of Michigan and University of Texas to drive the automation even forward, even further. For the two different types of maps, for the skeleton map, those areas that we hide within the map, we can introduce 6 different kinds of what we call assessment items, which are just basically ways for the students to complete the maps. And so these are things like multiple choice. We do provide a multiple choice where you can show distractor or other answers, optional answers for the students to choose from. A fill-in where you're expecting the students to come up with the content on their own. And what's nice is even with those 2 items, we can show that you can create both recognition and recall tasks for the students. So again, you're sort of mixing up those cognitive tasks. We have a drag and drop where they bring new content in, a connect to where they make the propositions, an error correct, which is a way of introducing misconceptions into the map to see if the students can find them and correct them. And then an arrowhead directionality. So if you had, sun revolves around earth, there's only one way that proposition should be read to make it a true proposition. So we haven't determined which way that arrowhead should go. On our builder map side, right now in our current version, we do use the master map, and then the student's task is to assemble it at that point. There's a couple other ways we could do this, but what's important to note is that the further you get away from using that master map, that is, the more content that the students are creating to include just building the maps from scratch, the harder it's going to be to provide automated support for evaluating those, right? So the things that Jim's doing to show conceptual change over time, again, fantastic way of going about it, but Jim has to go in and hand score or add comments to everybody's map. So there's ways to add, just a starter set of propositions, or maybe just the concepts, or concepts and linking phrases that are reusable. And so again, the harder it gets harder the way we go down that list. It gets harder to evaluate these things in a scalable way. But what we can do when we start with that master map is, of course, score each item. We can show things like also how long did it take the students to go through it? So additional metadata about them actually taking the assessment. We can even show sequencing. So it's possible to see which items students are answering earlier than others, which gives an indication about where they're at in terms of their learning. We can also then, with the builder maps, we can compare everybody's maps because we can amalgamate them. And because everybody's starting with the same Lego sets, we can show that these propositions were formed in more maps than not, or these propositions were missing, or students are also creating this extra proposition which wasn't in the master map, which gives us some indication of the overall understanding of the content. So everybody is welcome to go out and try out Sero. You can get your account at serolearn.com. My email is brian@serolearn.com. And I want to show you what Sero looks like now, but I want to also invite you to come take a look for yourself and then to engage with us as well. We're very interested in folks who want to give this a try in their programs. And I want to show you what Sero looks like, but also show you a couple other things. To include, by the way, the map that Charlie had noted in the chat. So there already exist in the world, for some of these problems, a lot of maps. right? So here's an example of the Sustaining Humans on Mars map. This was built by the Institute for Human and Machine Cognition using the tool that Jim was using earlier, CMAP tools. And so there's already a lot of content out there in maps that exist, and we can use those maps actually in Sero because we can actually import these directly. But as Jim showed, these maps connect to other maps. And so for this particular challenge problem, there's a whole gaggle of maps out there that we can make use of for assessment. And I want to say one more thing about assessment. So, in the ICE methodology, we want to see the learning occur over time, but up front, we kind of want to know where everybody's starting, right? So in a diagnostic sense, we can use Sero up front to say, given this content area, where are students starting? Where are they already pretty well steeped in the content, which might help guide them towards the areas where they're struggling, right? We can spend more time there. We can maybe focus more of our learning activities there. And so as they go through the activities and the learning processes that we want them to bring them to, we can also use these maps along the way to sort of assess where they're at. So have we seen the kind of growth that we would expect by this point? And where are the students at? They can use these as formative study aids as well to get their own, just view on where their own learning is in a given time. So I wanted to call your attention to those because, again, for this particular challenge problem, there's a lot of content out here on this very topic about space flight, but as well as some of the missions to Mars concept maps. There's quite a few of them available. Okay, so with that in mind, I want to now show you what Sero looks like, and I want to show you what it looks like from a student perspective first. So if I'm a student, this is my view of Sero. I'm going to see all the maps that have been assigned to me, as well as my own maps. We do have a CMAP editor where students can come in to create their own maps from scratch. Those don't get evaluated, at least not yet in Sero, but at some point in the future they will. But they can just come in and build their own maps. We also use CMAP tools here at my company. So, we can't actually do all the things that CMAP tools does in terms of connecting all those resources, but that's not really our focus. Our focus is really on assessment. So to show you what the two different maps look like, if I click on a skeleton map, this one's about just atoms, and students can see up front, what each of these assessment items are, and then how to go about completing them. So when we get into the assignment, then again, you're going to see a part skeleton map, right? You're going to see a concept map with some things that are missing or connections that are missing. So the way this works is the students find these things, and then they have, in this case, the multiple choice option. And as they fill these things in, the map starts to take shape, right? And so if this is an answer we want to add here, we can add it in. The map starts to take shape. Here we don't have an arrowhead, so the student's task for this one is to figure out which way that proposition should read to make a true proposition. This is an example of our Connect 2 where they have to complete that proposition. But what you'll notice here is this is not just a one-to-one sort of match. This is actually one to the map. It could connect anywhere. So the student's challenge is to think through states of matter are, which of these concepts would help complete that proposition in a sensible, meaningful way. If there's more than one connection, they keep getting the connections that they can make. Our drag and drop items, they're actually outside the map. And so the task here is to bring these in. Again, it's a one to anywhere in the map task. Where do these concepts fit that would help create a proposition? Now, both with the multiple choice as well as the drag and drops, you can introduce distractors, right? So the drag and drops can have distractors of their own, concepts that actually don't belong in the map, but the student has to wrestle with, does this even go in the map? And if so, where? The last one to show you then is our error correct, which is different than the others in that it's not visually cued. It's just the content of the proposition is incorrect. It creates a false proposition. So in this case, we know it's this one. And then when the students find them, they can click on them and correct them. So what we do with the maps is we take that master map and then we introduce these items throughout the map. And so that's an authoring process that shows the there's a lot of variety in the way that we can do these maps. There's also a range of difficulty we can introduce. So if you want a map that might be easier for your current assessment purpose, you might make a smaller map. You might add more multiple choice items than, say, error corrects. So there's a lot of flexibility in how to build these things out. And the beauty here is of course in the automation in terms of scoring these things. So the students take them and they get automatically scored. So they get a C right away. They get that feedback. And we can also show them, again, depending on your assessment purpose, we can also show them what the master map looks like. So if this is a formative activity, yes, they got a score, but maybe that score doesn't matter. What matters more is that they see the ones that they missed, and now they get to see the master map so that they can get that learning value as well. So the next one I'll show you then is an example of the Build-A-Map. And here, again, it's can use that same type of master map. Students get a view on how to take it. This map is going to be, though, generally smaller than you can do the skeleton maps with much larger maps just because, it's less for the students to sort of manage. With the builder maps, we tend to suggest, maps of 25 or so propositions or smaller are okay for the builder map. But here, again, the task is to build out the maps using the content that's available. So you have the concepts and then you have the linking phrases, and this allows the student to build that out on their own. Okay, in our current iteration, we just take that master map and break up the structure, put the concepts and linking phrases, and then have them build. You can also imagine cases where you may have a set of concepts and some linking phrases that are reusable. So, things like is increased by or is decreased by, especially in the physics content area, you can have reusable so that the students can wrestle with, should I use this once? Should I use it more than once? And again, because everybody's starting with the same set of Legos, we can now compare these maps once they produce them. And again, the value here, of course, is in the automation, in the scoring. The students can see which ones they got right, which ones they got wrong. And then ultimately, if you want them to see that master map, they can see it. So the last thing I'll show you is actually on the assessor side. This is what it's going to look like if you're an assessor and you're building these things. I'll just show you briefly also, we have created some maps based on the ICD methodology. And so we've already got maps built that express the methodology itself. So if you have an interest, for instance, in just as an assessment item, assessing the methodology as the students go through it, we have these built out in the form of skeleton maps. Again, these are fairly large maps, but if you want to also understand as your students are going through their program, do they understand the methodology as they're going through it, right? So you could assess on the content, but you could also assess on the methodology. So we've got several maps built against, a concept map version of the ICE methodology that we're happy to share with folks. But if I just go back and if I want to build a map from start to build my assessment. Your focus question, as Jim said, that's the most important thing up front. What is my focus question? And that's what we have you start with. I'll just say, what is my focus question now to get it in? You can choose if you want to do a build a map or a skeleton map. For the build a map, once you build that expert map, you're basically done. We just turn that into a build a map. I'll show you what the skeleton map looks like. You can create the maps from scratch in Sero if you want. You could actually import them from CMap tools. So if you wanted to make use of any of those Mars exploration maps, we just import those right into Sero and they become an assessment. For now, we'll just use one from a previous example. So you're going to come in, you've got your map. Again, you can create your propositions, you can edit or change these in any way. And then for the items themselves, you're simply going through selecting whether you want a concept, a linking phrase, or the arrowhead or the connecting lines to be the assessment item. So in this case, if I want that concept, I can now think, Is this a kind of concept that if I gave students a couple of choices, they might struggle with it? So does it make sense as a multiple choice item? Is this a kind of concept that students, it's fundamental to the understanding of the map? So I really expect that students should know this concept. They should know how to spell it. They should know how to state it, those sorts of things. If that's the case, then maybe you do a fill in. Is this a kind of thing where I've seen a lot of misconceptions in the past? So I want to see if students are also seeing the misconceptions, and then I might introduce it as an error correct. But if I want to make it a multiple choice, I can simply add my other options and author it this way. So this really does put all the assessment responsibility and ownership in the hands of the instructor. And then we start to see the map from the student perspective as we build it out. We then assign, our groups, our takers, whoever's going to take the map, and then we can format it to show, again, do I want them to see that master map? Do I want to show them the results? Just a quick note on our automated authoring. So what we're doing in that project is this initial map that's created, that's going to come straight out of text. So we're using some natural language processing to get the propositions and then walk through a process of sort of forming up that first map. We then also have a set of rules around where these items should go and what kind of item they should be. So we built those rules in as well so that you can actually have Sero determine, take a shot at creating my assessment items for me, and I'll go through and see which ones I like or add some new ones. So we're really scaffolding that authoring process up front. And again, for the build a map, once you have that master map, it's a click of the button to turn that into a map. I want to show you one other aspect here, and then I'll be happy to take some questions. But what I want to show you is what this looks like from the point of view of seeing the results. So as those student results come back, let me get in here real quick. Okay, so as the student results come back, you're going to be able to see those results. And if I just look at a couple of examples here, so here's, oh, that's not the one I wanted, sorry. If I look at a couple of results, yeah, that's what I want. So what you can see then is for every student's results, you see the overall, what your master map looked like, but then you can see each individual student map if you want, or you can see across everybody's maps, right? So we roll those up into a pie chart view. This ought to help you understand, again, depending on the content of your map and sort of where you put those items, where students are struggling across the map. Right. You can then, of course, see each individual student. So if you want to dive into their individual results, you can see what they're getting right or wrong too. But we really think that this kind of overarching view is really useful to show you, across everybody what their results look like. On the build a map, back to that notion of we're using the same Legos. So everybody gets the same set of Legos, but everybody's map's going to be different, right? They're all going to form different propositions. So what we do is we take that master map and we kind of just blow it out a little bit to make it a little larger so that we can now show across everybody's propositions that were formed, right? Because everybody's, again, going to form different maps. We don't actually care about the shape of the map, so they can put things on the left, right, it doesn't really matter. We care about the propositions they formed, okay? And so in this case, what we see is that as we move across consensus, that is, as we compare each student's map to the other students, we can see that some of these propositions, only a couple of them, a lot of students were getting. Okay, so this tells us that students seem to understand this part of the content, right? Because we've got 5 out of students got these propositions, included them in their maps. Okay, and then in this particular case, we can also see the incorrect. And so as we move across the consensus, we can see that not a lot of students were getting this one wrong, right? So that is an indication to us that that the students, again, seem to understand that. We can also show missing. So which propositions are students just simply not including in their map? Again, that points to a major gap that students need to work on. And then we can also show the extras. And so extras can be everything from a guess, students weren't quite sure, so they just sort of attach things, to if a lot of students are having that same extra proposition appear, then a lot of them seem to share the idea that this proposition should be in the map, right? So we can deal with that misconception as well. And another really nice thing that we have that's available then is as we move further in our project with the Air Force, we've been building out an approach to be able to show students compared to other students. And I just want to make sure I get the right map here. And so what this looks like is if we take everybody's map and do that, comparison of all the propositions, we can also then compare individual students with each other. So we worked on a scatter plot view here that basically shows students compared to each other. Again, same set of Legos, but what do their maps look like that they built? And then how do those maps compare? So we're able to see that some students' maps look very similar to each other. And then we can also gauge their distance from the master map. So is it the case that students' maps look a lot alike, but they're all wrong? Or do we have a cluster of students whose maps look a lot alike because they're very close to the master map as well? So as a diagnostic tool to think about, how do I want to start to build groups? If that's a concern for your program, you can mix and match your students here. If you've got students who are already, at least with regard to this particular mental model, already pretty similar, maybe you want to mix them up in terms of the groups, right? And so so this gives us yet another view, a powerful kind of scalable view to really see across all the students' work. So I'm going to go ahead and stop at that point. I'm happy to take any questions. And then again, thanks everybody for including us in the presentation today.
Can everybody hear me? Okay. Do we have any questions for Jim or Brian?
Can I point out, for those that are in Brazil, you have a lively CMAP community. Paulo Correa, I'm probably butchering his name.
That's right.
Yeah, University of Sao Paulo, right? I think he's based out of, I put the link in the chat to his ResearchGate profile so you can find out more though.
Yeah, that's a great idea, Jim. We've been working with Paulo actually for a couple of years. Our error correct item in the skeleton maps actually came from his work. So they've done a lot of work to understand how CMAPs with errors can be useful in correcting those misconceptions.
Excellent. Do we have any questions? I'm sure there will be questions as people view it. Oh, wait, Ada has a question. Ada?
Hi, this is Timothy again. Do you have a set of maps already available? Like I'm imagining the usefulness of this for curriculum development. And I wanted to know if you already had basically curriculum developed that are already mapped out.
So for using Insero, the map that I showed about Mars exploration, there are a lot of those available. Those were developed by IHMC with folks from NASA. So for this particular application, yes, there actually is are maps you can use for the purpose. We again, with our automation tools, that's one of the sort of long poles in the tent that we're trying to help in terms of the efficiency, so that if you had learning content, you're going to be able to bring that in as text into Xero and then quickly put these maps together. But again, we're really trying to kind of democratize, if you will, the assessment process so that the instructors, depending on their assessment need, can have a suite of concept mapping tools available to them that are going to help them quickly pull together an assessment, either at the diagnostic, formative, or even summative level. It's worth noting here that the National Assessment of Educational Progress for the Science Framework, which is given at grades 4, 8, and 12, it actually calls for using concept maps as an interactive computer task to do summative assessment. So there is, there's standardized testing, precedents for doing this sort of thing. For us, we're trying to sort of build to both levels, so that scalable, large scale assessment, but also tools that students and teachers can use in the classroom too.
Okay, thank you.
Okay, Ada?
That was it. Sorry, we're together here, Tim and I. Thanks.
Okay, any other questions on CMAPs? What I'm going to do is, I think someone had a question about what's the difference between CMAPs and what Ali Devek presented in OPM. And I input the wrong CMAP before. I have a CMAP that I just input in the chat box. And that's kind of the CMAP I created, which includes some of the OPM model that Ali Devek created. And so you could use them kind of interchangeably, I think. Take a look. And right now, I think we're getting ready to actually have the competition, or to have the teachers, the teams demonstrate what they created. And I want to thank Brian and James, and they're welcome to follow along. Do we have any team that wants to go first? I think, Ada, you mentioned someone in Mexico sent something to.
So we sent Timothy's code to Andrew, and we got some feedback. So I don't know what else. I mean, we can go first, but I don't know if this is something we want to show.
Okay, wait a minute. Andrew's here. Go ahead.
So I actually just looked at the code that you just recently sent, and I sent back some more feedback on that. I don't know if y'all have had a chance to look at that feedback, but certainly since y'all are working on this, we want to help you with that and whatnot. So go ahead and take a look at that email I just sent, and then you can either email me directly or hop here on Zoom and ask a question. I think, Charlie, are we going to try to have people show if they did anything in the simulator, and then likewise we'll also run programs?
Okay, that's a good question. Who has used the simulator? Who's experimented with the simulator and wants to demonstrate what they learned by doing that? Do we have anyone online that would like to share what they've done? Very good point. I don't see any hands being raised. So I think what we'll do is we'll take.
So I've only had one person submit that.
Okay, we have a couple of team members here that have been working. Does anyone want to go first?
Well,
Team Mexico? Okay.
So I can run code that they just sent me.
Sounds good. So we're going to take, Andy, you want to take it away?
Yes. So I guess Timothy sent me some code. They're down in Mexico, and we can run that on here real quick just to see what it's doing. Now, the way that you guys modified your program, you didn't just change the random direction function that I had in there originally. You added another function. And then when I gave you some feedback on that, you went in and basically called the random direction function at the beginning of your new function. Well, what that's causing is a situation where the only thing that's happening is that original random direction function is going. And I don't know if we'll see the robot here get stuck in a corner or anything like that, but basically it's still essentially just using that original random function. So what we wanted to have happen was for you to actually modify that random function and improve upon it. So I sent you back an email that's got some feedback on that. And here you can see where it's actually bouncing around in this corner. Eventually it'll get out of it. But it's essentially still just using that same random function. It's never getting into your if statement. So go ahead and check out the feedback that I sent on the email. And I think what we'll do is we'll give you guys a little bit more time to think about that and make a change to it. But then I want to go ahead and send out what my solution to this was so that you can see that. And then I want to move on to the next part of this where we add in actually identifying whether we're on top of the blue paper or not. So we'll take about 15 minutes or so, give you guys a chance to modify that. And if you send something back, I'll run that on here, and then we'll go ahead and put up my solution for what it was and move on to the next part of the challenge.
Thank you, Andrew. It's really cool to see, and thank you for the feedback. We're working on it.
Okay, we have 15 minutes. We'll be back.
Yeah, as a robotist, I must say something about the situation. Congratulations, Mexico. It's difficult to work without the robot to be able to test the code. This is a very complex task without having the hardware to be able to see. Even me on the simulation, when I was working yesterday to try to implement the challenge, I was getting out some stupid bugs, and that's the part of the learning thing. You compile it. Oh, what have I done? Of course, it doesn't work, and you don't have this possibility if you don't have the robot on your hand on the way to try out. So congratulations for for what you're doing.
Yes, thank you, Eric. We also misinterpreted some of the blocks, the meaning of the blocks, but so it's really good to have this. Thank you for putting it together, all the people involved, to experiment with it.
Yeah, for the blocks, we've been working, I've been working with NTU, but NTU developed those blocks, and they had to wait for me to go further in the development of the controller on the robot side to be able to work. So they were very pressed by time. We were all pressed by time, the short amount of time to develop that. So yesterday, Gilmar, I think everybody saw on the community, posted some documentation that he wrote at the last minute. Congratulations, Gilmar. I had a look, and this is pretty much what you need to go further and understand better, and not having, because I run through similar issues of interpretation of the blocks. It was the same. So the material Jim proposed is actually very helpful.
We're gonna look at it. Thank you so much for all your efforts.
Thank you, Eric. And Ida, I think I have answered Timothy in the email. So I've provided this documentation into the email too. Okay.
Yes, we saw that. We just haven't had a chance to run it.
Okay, no problem. Thank you.
Thank you.
I can share what I managed to do in Finland. Not very proud of it because, well, maybe I should be proud. I don't know. I made the robot do a few flips, I think, because I forgot to put there some distance blocks. So it just went to the wall, and then it like went on top of the wall, and then it just flipped.
Isn't it a part of the process of learning that you described?
Yes. And I have to tell you, I was so happy when that happened in the simulation, because I'm not sure if I would dare to do that in the real life, you know. So seeing it kind of flip, I was like jumping here. Oh, what's happening? Yeah, but then I couldn't go back to fix it. It was quite a bit getting late, and I was then getting busy. But yeah, I really enjoyed the playing in the simulator. So thank you for preparing it for us.
Hopefully the student will like it too. And I'm sure that Andrew is pretty happy also with the possibility of having a simulator now, because breaking robots is not really the right thing to do. It's better to break the simulation one. Oh, I wanted to add also for later on, I guess, if you want to do, there is, so we have the E of EPIC for the trial of the robot, but I added the B, I, and C also as a maze. There is a scene also, I think it's available in the simulation. If you change the what is the name of it? The name of the file. There's a new file that you can download, and then you have the EPIC. So this is even more challenging to address. But if you're interested afterwards, because obviously time is the real EPIC challenge here, is the short amount of time to be able to do the thing. But you can change, I think, when you load the robot, You load the robot. Where is it? I'm looking for the stuff. I had it. You are loading a scene, but you can load another one. Scene. Where is it? Oh, I don't have it anymore. And this scene is enabling you to. It's Epic Challenge 2.ttt. If you do the load scene first. And if you change that to Epic Challenge 2, I don't know if it's still there. Let me verify. There is a even more challenging pass that you can try your exploration software.
Okay. If someone needs to test more this platform, we can provide before after this challenge. Just send an email, and we will talk about this.
Oh yeah, sorry. It's I forgot. It's on the cloud, and the cloud is not available for.
Yeah.
I forgot about this detail.
We can provide access after the challenge. Just send us email, and we will provide this for 2 or 3 days as a demo.
Yeah, the integration is so seamless that I forgot it was on the cloud. You guys did a great job at the NTU with the cloud interface. It runs very smoothly, just like in my own VREP local installation.
Mexico there? Ada or Timothy, are y'all there?
Yes.
Hey, so I looked at the code you just sent me. I think it'll work. I went ahead, I sent you another email saying to add in that robot.run. I went ahead and added that in for you.
Yeah,
So as soon as
just-
you guys get off the course, I'll go ahead and run your code and let you guys see what happens with it. All right.
Okay. So I just put robot.run above each if statement. Is that what it?
Yeah, so you figured out exactly what needed to happen in the random direction as far as making that work with your other function. I'm pretty sure your logic will work. It's different from the logic that I used, but I think it will still work correctly. So we'll go ahead and get the overhead shot of the track here and throw your robot on there, all right?
All right, thank you.
Hey, Trey, can we go to the overhead shot of this? Yeah, that'll work. Okay, so hopefully it should get out of this here. There we go. Yeah. It's just getting a little bit off going straight, but that's okay. It'll probably touch the wall and straighten itself out. Okay, so here's one spot where the way that y'all did it, instead of actually, no, okay, you're doing 180 degrees here. Perfect. That will work. All right, so y'all's code does work right. I think we'll give a couple more minutes and then I'll get up and I'll throw the code up on the screen for what the next part of the challenge is, and we'll give everybody a little bit of time to do that. The teams here have already, they've had the advantage of being able to work with me while we're doing other parts of the conference, so they've already completed that part, but we'll get it up for you guys here in a minute and go from there. So good job.
Thank you so much.
Thank you.
Okay, so was there anybody, we had a team from Mexico that sent some code in and successfully completed the first part of the challenge. Is there anybody else that is still working on the first part of the challenge that's planning on sending the code in? I'm not seeing chat. Did anybody say anything in chat? Okay, well, I'll go ahead and take your silence as a no. There's nobody else working on it. So we'll go ahead and I'll go through what my solution to the first challenge was, and then we'll get into the second part of the challenge. So again, we've got all this same code here at the top. The loop function didn't really need to change, although we did have one team that did make a modification here. But essentially what we did, got rid of that while loop. So we didn't need a loop to go through that every time. We knew that after we made one random decision, there was only a few options for us to go through. So getting rid of the while loop was the correct thing to do. Calling this random number once at the beginning of your function and not continually calling it again is the other thing. And then going through and using if statements to pick out which way you've gone and whether you need to turn the next way. Now, Timothy, one of the things you guys did was you always, if the first way wasn't free, you always chose to go right after that. And the way that you set your algorithm up would work, and it would always get you out of, you know, whatever corner you were in. But it did have a little bit of an inefficiency in that it could have a third time where it wasn't really facing the right direction. You had to spin around 180 degrees again. What I chose to do was use the random direction that I had picked the first time, but go the opposite way. So the first time I pick a random number, depending on whether it comes back being odd or even, I will go right or left. And then moving forward, I'll do the opposite of that. And then the last time I've used that same opposite from the first one, except I go 90 degrees. And so that always gets us to, we only have three choices, you know, 3 attempts and we're moving again. But what you guys did worked, and, you know, that did solve the solution. So with that, we will move on to the next part of the challenge. So the next part of the challenge, we want to, you know, use that random exploration algorithm that we had, and then also incorporate in the ability to find water or find that blue spot on our track. So the program is going to start off essentially the same thing. One thing you'll notice is at the beginning, we're no longer commenting out this use color function. So that's going to tell our library that we do actually want to use the color sensor. I've added in a couple more commands here that you can use, and these are what you're going to use to read the values off of the color sensor. Now, this sensor doesn't actually return a red, green, blue value like you would have in a computer software, you know, 0 to 255 for each of those values. What it's doing is it's actually, it has one channel that's clear, and so there's no filtering on it, and it's basically just going to return a luminosity value. So how bright is the light that's getting to that sensor? And then it has one with a red filter on it, one with a green filter on it, and one with a blue filter on it. And so if you have a very bright light, you can still have relatively high numbers on red and green, even though you're on top of a blue surface. Likewise, there's situations where blue light goes through a green filter, so you could still see a lot of blue through your green filter. So if you're on blue, you're going to still have a relatively high number on green, and red's the one that's really going to drop off. So they don't quite work like a regular color on a computer. They're a little bit different, and because of that, I've gone ahead and added in a function, look for water. And so what this is going to do is it's going to go through, and it's basically just going to use this if statement right here to determine whether it's over that blue patch of paper or not. And I'm taking advantage of a thing. The surface in this track is a shiny, kind of glossy surface, and I've got an LED under the robot. And that makes it so that when I'm on that white shiny surface, I'm always getting a very high number. And then I know that, you know, I did some testing with it. In an ideal situation, you would want to take that color sensor and test it on multiple different surfaces and see what numbers you're actually getting and do a little bit better value of just picking out the blue paper. In this particular instance, I haven't tested it, but I'm pretty sure if we put a purple paper on there, it would still trigger it. And I could see some other colors, you know, possibly still making this logic think that it was true, right? But basically what I did was I looked at it and I said, okay, my red and my green are always coming in about under 8, you know, one of them's, I think the red comes in about 200 or 300, and the green comes in about 550 to 650. So 800 was a good number. Usually the blue is still over 1,000. So this seems to work fairly well for the scenario we're in. In a real situation, you would want to tune this a little bit better and make sure you're doing just blue. So anyhow, what this look for water function does is it comes in and it makes this variable that's just a Boolean. It sets it to false. You know, you first call it, it has not found water. It runs this check. If it's on top of the blue, it sets found water to true, and then it returns found water. So basically, you can use this function as a true or false. You know, either you're on top of the blue square or you're not. So back here in our loop function, okay, I've set up an if statement for you that's going to encompass everything. And this is going to say, okay, should I keep looking? Now, the reason we're doing this is because in Arduino, we have this loop function that's going to run forever. I want to always still call this robot function because it's handling the battery charger on the board. And so I want to have a way where once we found water, we stop looking for it. So essentially what we're going to do is we're going to set this flag to false once we found water. And then this if statement is never going to do anything after that. So basically after that, the robot will just sit there. So I've gone ahead and set that up for you. We've got that same piece of code we had before where we move forward and then we use a while loop to continue going until we reach our stop distance. And then we put the motors in standby and we wait 5 seconds. So here in this comment block, you're going to need to change what's right here and essentially add back your random turn function. So you're going to want to find new random directions once you've come to a wall, the same exact way you did it before. Or I've included in at the very bottom here, my random direction function. So you're more than welcome to copy in your own and the method that you used in your program, or you could just use what I have here, whatever works easier for you. So you want to do that, but you're also going to want to have a check where you call looking for water. And if it comes back true, you want to set keep looking to false. Okay. And there should be some, decent explanations in here on what you're trying to do. The only changes you really need to make are going to be right here. You're essentially just going to add that code to do your random search algorithm or random explore algorithm, and then actually do the check on the water. And again, the check on the water, you just use looking for water. And then if that comes back true, set keep looking to false. And then you'll also want to call a victory dance. So we need to have a way to identify when your robot has found water or thinks that it found water. And rather than programming it to go back to home, which is going to be a little bit tedious, we want you to just call this victory dance function. So this is already built in here. I've got a couple dance commands beneath here. But basically what we're going to do is we're going to set the speed of the robot to 100 because we want to go fast for dancing. We're not really worried about precision. And we're also going to make pivoting go at full power because, again, we want to look cool and dance quick and not worry too much about precision here. And so then basically you will just add in a series of dance moves here to be your victory dance. So that's this last part of the challenge. And I'll send the code out on the Zoom meeting, just like I did yesterday. I'll get that out in the next couple minutes. And then I'll also post a link to that folder on the NTU website. So do you guys have any questions on that? No questions? Are y'all still there?
Yes, maybe after we play with your code, we will have questions.
Okay. All right, good. So I'll go ahead and get that sent out, the code. Again, I'll put it in the Zoom chat here in a moment. I just got to put it in the Google Drive. And then I'll also share the link again on the NTU website.
Wait a minute. Okay. Okay. How's everybody doing out there online? Flavio, you're gonna. I see you have a chat. You want to post the block code in the chat box? Is that right?
Yeah, Charles, what do you think?
Did you hear that, Andrew? They want to put the block code in the chat box. Will you be able to? Would that be okay? And do you want them to pull it up and run it in the simulator? Oh, here we go. I'm sitting at my desk. So is this block code, this is for the simulator, Flavio?
Yes. What do you think? We can post here, or is too much?
No, you could go ahead and post it. And what we could do is we could save this chat box.
Okay. Okay.
Uh-oh, wait a minute. I'm hearing from people behind me that if you can upload the file or send the file. Could you email it to Andrew?
Yes. Yeah.
Okay.
Is that text file? Okay, I sent to Andrew.
Okay. Flavio, we're thinking that, I don't know, we're thinking of closing things down for the symposium, for the workshop. What are your thoughts?
Just a second. Are you listening?
Yes.
Dennis? Just a sec. Dennis?
Okay. Hi guys. I don't know if you guys can hear us.
Yeah.
But we are very excited here in Brazil and very thankful also. So we accompanied all the groups around the world solving the problems. We saw some groups with some major or bigger issues that Flavio and Gilmar were helping along the weekend. And we really don't have much to talk. Unfortunately, our groups in Brazil couldn't participate because of the lockdown. But the government and some major people here in Brazil, some VIP people here in Brazil, they are very excited to learn more about our solution, and maybe we can talk about this later during the week. So it's just a lot of pleasure to have participated with you guys. And we are eager to see the solutions of the teams around the world.
No, I think that would be great. I think, and you know, this was a challenge. This was an epic challenge, trying to put everything together. And we just started working together as a team, and it was amazing to me to see how much we were able to accomplish in a short amount of time. We have some great partnerships. Everyone had a chance to see some of the different teams and partners that we're working with, how we're pulling this all together. Our friends at Space Trek, Zero Learn, One Grow, Siemens Corporation, And I believe when we design the 1-week workshops, I think we'll be much further along. I think it will be a much better learning experience because we're going to dive deeper into the methodology, and we could work one-to-one, so to speak, with the individual schools and the individual educators. And so if folks in Brazil are interested in doing this, and teams of schools in Brazil are interested in doing this, we have to search out and get those teams of schools at the high school, community college, university level in the United States, in regions in the United States and around the world. And so that's what we plan to do before school starts next year. And so we have lots to do before then. And but it's very promising. Any feedback from any of the other educators that have participated?
Hi, this is Aida. Thank you very much to everybody for presenting their tools. They're very interesting, and we look forward to trying those. There's a lot to digest, right? It was a lot of material, but we've been taking notes, and we will send feedback as well, maybe a little summary. And we plan to gather with all the educators in Mexico to hear their views as well, because through the chat and through the WhatsApp, it's a little bit difficult. We'll send you feedback.
Sounds good. We will get together. We will have a meeting. We'll get back together in a couple of weeks or so. Anna, how about Finland? You're going to be working with folks in Finland.
Yes, so this week was our finals week here. So a lot of teachers were very busy, so they couldn't join today or this weekend, but we hope to have them in the following weeks or when we next time have this event. And yes, it was definitely my pleasure to share with you, everything we have learned over the years. And I really, really hope that we get to work together with, with the whole world. So personally, again, feeling very, very excited. Thank you, Charlie, for organizing all these amazing speakers, bringing them together, telling us all these amazing, inspiring stories. So last night, it was actually really hard to sleep because I've been all the time, thinking about all these great things we are going to do in the future. So I'm really, really looking forward to it. And I hope that everybody else also got inspired, and that we can work together in the future. So greetings from here.
Yep. I want to thank all,
also in person soon.
Absolutely. I want to give a great thanks to, of course, the team at Epic Education Foundation that made this happen, our partners, our partnering schools, our sponsors, Tamer Space, Honeybee Robotics, IQ4, and all our sponsors that made this happen. And I look forward to working with you in the near future. Thank you very much. And thanks to our friends at the Astronaut Memorial Foundation. This is an amazing space. And did we want to show them, Joe, take them on a video tour? As we close out, what we'll do is we'll take you on a little virtual walking tour of the facility that's just going to be opening up here, which is a regolith pit, a large regolith pit, which has 2 chambers where multiple robots could be exploring and attacking the challenge simultaneously. So we're getting ready. We're going to give you a quick walking tour of the facility here. And the hope is that the end of next school year, we will have hundreds of students and teachers here competing, or not competing, but collaborating on solving challenges, on robotic challenges on the surface of the moon, simulated surface of the moon. Okay, so we're going to close out with a quick walking tour. Someone's getting it up on their phone. We're going to show you the facility. Oh, we could take a computer. I could take my computer. Yeah, I guess I could take my computer, right? Or is he using the camera up there? He's not using the camera on my computer. Wait a minute, I should be able to show, wait a minute, let me see. Using the wrong camera. Okay, wait a minute, let me see. This is getting too difficult. I don't think so. We didn't plan this. I'm killing the technical crew here. I think we should just pull it up on the telephone. On the phone. It's not working. Look, it won't let me take the camera. It won't let me choose the camera. I see the camera here.
We can see you, Charles. It's possible to see you, like the camera of your computer right now.
Yeah. Can you see me?
Yes, 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 yes.
Yes, we can.
Yes. Yes, okay.
All right. I could take my computer.
Yes, we can see you.
No, but you can't see me if I walk off the stage, right?
Yes, we can.
Now you can. Now you can. Okay.
Yeah.
Okay. So let me see. If I use the sound on my computer,
I think
keep it like it is. Keep it like it is. They tell me, okay, I'll take my computer and we're walking through the facility. It's an amazing hall. You can see yourself on the big screen back there, two huge big screens.
Cool.
We're going to go. This is the Astronaut Memorial Foundation.
There's
And
Joe
next
behind you.
Right
Hi,
next
Joe.
to the Astronaut Memorial Foundation is Space Trek. And then we're going to take you into the regolith pit right here, where hopefully in July, it will be filled with regolith. Okay, so this is, you can see that that's the size of the facility here. And we'll have 2 chambers where students will be competing in two different sections, robots. It has to have very strict safety requirements because the regolith simulant is kind of toxic. And so we have to follow those safety procedures, have negative pressure cleaning facilities to clean the air to make sure. So it's a big deal. And that's what we have to look forward to. Hopefully in July. How's that sound?
Amazing.
I can't hear you. Okay, let me get back in the main room so I could hear you. And I just wanted to give you a little preview. But the other thing is when you get to visit Kennedy Space Center, hopefully we won't have any problems with COVID. And folks will have access to the visitors complex, and maybe we can get some tours of the actual facility. And if we're really lucky, maybe the students will get to see a SpaceX launch or an SLS launch. So that's what we're shooting for next year, guys. I want to thank you once again very much. And we'll be talking to you shortly. Thank you very much.
Thank you, Charles. Thank you, everybody.
Thank you, Charlie.
It was great.
Great event.
Thank you.
Congratulations to
Charlie.
everybody. Bye-bye.
All right.
Thank you.
Bye-bye.
And also, we'll be sending you the recordings. We'll send you the link for the recorded lessons. See you, Ada.
Yeah, okay. In the chat,
Dennis,
please.
Flavio.
Bye-bye.
Bye-bye. Bye, Charles.
Bye-bye.
Bye, everybody.
Success. Yeah, we'll get this down.